Welcome to Fuzz Fest. We're gonna set up for our first talk, which is gonna be from Dacian. I'm gonna hype him up in a second. Let's just sort out the screen sharing. Please, Dacian, start sharing your screen. Everybody prepare to lock in. This is the first talk of Fuzz Fest. Welcome. And when I saw this talk at the DeFi Security Summit, I knew just had to do it again. The room was packed. The talk was extremely well received, and unfortunately, it was never recorded. So this is the recorded version of that talk. He's a prolific smart contract security researcher and auditor for Cyframe. He has protected over $3 billion in TVL. You know him from some of the most in-depth, highly shared, published articles in the space. This is finding high severities using invariant fuzz testing. Welcome, Dacian, to Fuzz Fest.
Wow, Alex, thank you so much for that intro, man. I'm so hyped up. You know, my heart is racing now. And thank you so much to everyone for being here with us as well. And so this is my talk. We'll get right into it. So it's called Find Highs Before External Auditors using invariant fuzz testing and now formal verification. And the whole point of this talk was that, we have a lot of really good tools, but in the private audits that we get coming through, a lot of those tools, they're not being used. So it'd be great if we could get those tools closer to the developers so that they could use those tools. And by doing so, they could actually find a lot of issues before they make it to the external audit. This is one of the observations that I've had, that many of the findings that external auditors find, they could have actually been found by the protocol themselves using tools like invariant fuzz testing. And one of the benefits of this is that it doesn't require developing an attacker mindset or any other auditor specific skills, right? But it does require learning to think in invariance. But the good news is that this is something that everyone can do. Everyone can acquire this skill. And if you do it, it'll make you a better developer and a better auditor as well. And there's also briefly an economic consideration of this as well, is that the developer who's written the protocol, they already have the full context of the protocol and they know its important properties. So it's actually a lot more cost effective for protocol developers to implement fuzzing suites themselves as well, prior to engaging more expensive external audit firms. So if you're an auditor, you're going to say, what's in it for me? What's in it for me? Well, what's in it for you is to learn a new thinking method that will allow you to view the protocol that you're analyzing with a whole new lens, and you learn to think in invariance. And the good news is that this will enable you to find new bugs that otherwise you would have missed before. So you can think of this as just another tool in your toolbox, another way to get cool findings. And the good news is that everyone can learn this. So later on, there's going to be some really complicated stuff that some people might try and teach you. But the good news is that I'm not going to do any of that. Everything that I'm going to present here today, I learned from scratch and I learned for free. And all it takes to learn this is you need an internet connection, you need a computing device, and you need some time and the desire, the drive, the willpower. And if you have all those things, then the good news is that you can learn this and you can do everything that I have done here, and you can find the same bugs that I have found. So literally everyone can do this. And I'm going to show you just how powerful this technique is, that you can define very simple invariants that can actually find very complicated bugs. And it really is like magic, like a superpower once you start to think in this way. So thinking in invariance, where do we start? Well, this is a simple framework that I've put together. So I think of smart contracts in terms of life cycles, and I also think in terms of black box and white box, right? So what is an invariant? Well, for us, for our purpose, an invariant is going to be a useful protocol-specific property that must remain true. And we've got two ways to implement it. In Echidna and Medusa, it's going to be a function that returns true if the property holds, false otherwise. And in Foundry, it's going to be a function that contains one or more assertions. And then in Certora, we've got rules and invariants using their own programming language as well. Now, what is the smart contract lifecycle? Well, I like to break it down into three general life cycles. So the first bit is the construction or the initialization phase. The next life cycle, the next stage of life is the regular functioning of that smart contract. And then some contracts optionally have an end state at which point they will stop doing anything. And so what we want to get into the habit of doing mentally is we want to identify each of these phases of the smart contract's life cycle and then try to find useful properties that should hold true during these phases. Now, what about black box and white box? Well, a black box that's a property that we can glean from the protocol's design or documentation, but without needing to know the internals of how the protocol actually implements functionality. And now, as an auditor, you might be thinking, oh, that's crazy. Like the first thing I do is I read the code, bro. Just read the code, right? That's how I get all my findings. How am I going to ever find things without reading the code? Well, the good news is I'm going to show you today that most of the invariants that we're going to define, they're almost all black box invariants, right? So this is one of the amazing things that if you learn to think in this way, you actually don't even need to read the code to get high value findings. It really is amazing. It really is amazing. There's also something called black box testing. Typically, black box testing is something that happens in the traditional software world. So when I was a software engineer working for soulless multi-billion-dollar companies, back when $1 billion meant something before we started printing trillions, but when we used to write our code, we used to test our code, then our code would go to a test team, and then it would go to a black box team that would test our code without actually reading the code at all. They would do all sorts of crazy things, right? So that's the idea of black box testing. Well, fuzzing, in a way, can be a form of black box testing where you can define useful properties based on the system's documentation or specifications. And then the fuzzer itself kind of does the black box testing for you by probing and trying the system in many different ways. Now, white box are properties that we implement based upon the internal knowledge of how the smart contract works, right? That's by reading the code, looking at storage, looking at memory, looking at how functions manipulate the state of the protocol. And it's useful to have both of these in mind, right, as we look at the contract's lifecycle. Now we can get a little bit more specific, right? So we can break down invariants into sort of more advanced classes. So we'll start with a basic invariant. A basic invariant is just an obvious sanity check, right? So that is, for example, you're initializing a contract. So the sum of initial allocated points must equal to the total points, right? So that's an initialization invariant. It's a white box invariant, right? Some invariants, they're going to be cheap to implement. And when we say cheap, we're talking about the gas cost, right? They're going to be cheap to implement. And if an invariant is cheap to implement, as a developer, we should actually implement that invariant straight in the code. Now, other invariants, they're going to be expensive and indeed very expensive to implement, which means that it's impossible to implement them in our code. But the good news is that we can implement them in our invariant fuzz testing suite. An example of that would be, for example, we're going to see an example later on. All right. Now, what's an advanced invariant? Well, one type that can be very useful is relationships between different storage locations. Right. So here's one that is very useful to keep in mind that is a very high value one that will let you get good findings. So the sum of all values in a given mapping X must equal to Y stored elsewhere in storage. Right. So often you'll see a smart contract protocol and you have a mapping of, say, addresses to balances. And then there'll be another storage location that'll be called, like, say, total points or total balances. Now, in a purely mathematical way, the sum of all the values in the mapping should always be equal to the total, right? But because it's cost prohibitive to check that at runtime, typically smart contracts will make sure that they update the total whenever they change the mapping value. But that can go wrong, and so a useful property to see if that actually checks out, if it actually holds. And this is a regular functioning. It's something during the contract's lifecycle. And it's a white box invariant because we're looking at the internals of the smart contract and how it's written. Another example is that all addresses present in an enumerable set X must also exist as keys in a mapping Y. Again, this is another regular functioning, a white box invariant. And this is another common pattern that you'll see in smart contract protocols. And that's where you have interrelated data structures. So that's where you have data structures that reference keys and values and identifiers across multiple data structures. And so a very useful invariant property is to see whether those references remain accurate. So for example, if there's a uniqueness property that has to hold true, can the fuzzer find a state where it will violate that uniqueness property? And that could lead to quite a nice exploit. A second category of advanced invariance is when monetary value is stored in a contract and it's related to the concept of solvency. So for example, let's say that we've got a contract that distributes tokens. Well, when the contract's token distribution is complete, the contract should have a zero balance, right? This is an end state, it's an end of life cycle, and it's a black box. Why? Because we don't have to care about how the contract actually distributes it. We don't actually need to read the code for how the contract distributes tokens at all. The only thing we care about is that whenever it's finished, whenever it goes into the end state, there should be no tokens remaining in the contract. Another one would be that a contract should always have enough tokens to cover liabilities, right? So what does that mean? Well, it means that, for example, if a contract owes money, it owes financial resources to users. For example, they could be stakers and they're due rewards or whatever it might be, then the contract should always have enough tokens to cover those liabilities, right? And so then we want to check if there could be any way for that to be violated, which could lead to quite a nasty exploit, for example, the contract being drained. Another class of useful advanced invariants are logical invariants. So logical invariants are, for example, here an account with an active borrower can't exit a market, right? So that's where an account enters a market in a lending and borrowing protocol, and then it takes out a loan, and then before it repays the loan, it shouldn't be able to exit the market, right? This is a regular functioning, and it's a black box because we don't really care how that's implemented. We just know that this has to be true. Another one is that a protocol should never enter a state where a borrower can't repay a loan but can be liquidated. Again, another regular black box invariant. These logical invariants can be very useful as well to find states that a smart contract system should not be able to enter. And the last category that we'll look at today is the denial of service invariant. So this is a very useful, perhaps not as well known tool in the Fuzzers toolbox. And that's where we can use fuzz tests to detect very subtle bugs due to unexpected reverts. For example, due to panic reverts or all sorts of crazy things that can happen from access array out of bounds, underflow, overflow. And this is where certain functions revert when they shouldn't be. So for example, in many protocols, liquidation is a core function that should almost never revert unless it's for a very specific reason. So we would want to use this denial of service fuzzer on the liquidation function to see if we can find some really weird state where it reverts when it shouldn't. And if that's a lot to take in, don't worry, because we're going to see examples of all of these as we go through. Now, the next thing to consider when building fuzzers is whether we use handlers or no handlers. So a handler is just a function that wraps an underlying fuzzer function. And so fuzzers, they can use handler functions to wrap the underlying functions from the target contract being fuzzed in order to satisfy preconditions. Or the other option is that the fuzzer can have no handlers, and that lets the fuzzer explore more freely. So what is the trade-off here? Well, if we have no handlers, then the search space can be too large, so the fuzzer, it might not have enough time to find that invariant breaking sequence. But the trade-off here is that without any handlers, we can have many wasted runs due to triple reverts because there's require statements that will just fail over and over again. With handlers, we can eliminate wasted runs due to those triple reverts by satisfying the underlying function preconditions. But the trade-off here is that we can restrict the search space too much so that we can miss some attack paths. And typically what most fuzzers will do is that they will use handlers, but they'll use handlers judiciously, taking care not to constrain the search space too much. So here we're going to see some examples of invariants. And so we're going to see an example of going from the code to the invariant, and then we're going to see a lot of examples of going from a specification to an invariant. And the first example, this is from a well-known CTF from Damn Vulnerable DeFi, but everything else here, everything else after the first one, these are all simplified versions of real findings from my private audits at Cypher. So this is real world stuff. Like this is stuff that if you learn this stuff and apply it, you can find high value vulnerabilities in real world audits and deliver a lot of value for your clients. And if you're a developer, then you can find those vulnerabilities before you go to the external auditor and harden your code base even more. So here we go. This is the Damn Vulnerable DeFi one, and this is like a denial of service challenge where a user should always be able to take a flash loan. as long as there is enough ETH in the pool, right? So we've got two ways to implement this. We've got the code there on the right side, that function, the flashloan function. And we can do a black box invariant. That's where we don't really care how that's implemented. We can just call it and make sure that it asserts true afterwards, that it doesn't revert. It's a very generic invariant. It's harder for fuzzers to break, but all three fuzzers that we use, Echidna, Medusa, and Foundry, can break this. And the other one is the white box invariant, right? So here we're actually looking at the implementation of the function, and we can see that assert statement there, that pool balance is equal to balance before. That gives us kind of a hint, so we can give that hint to our fuzzer as well. And this kind of makes it easier to break because it kind of guides the fuzzer a bit more on what it should target. But this is a simple example of how we would sort of classify black box and white box invariants. This is the only CTF. Everything else after this is real. So here we can see the same solution, but using Satora. This is using Satora's formal verification language. So this is formal verification as opposed to fuzzing, another very useful tool in your toolbox. So the beauty of Satora is that there's no setup, there's no handlers, there's no fuzzer infrastructure required. It's very concise. So although we showed you here, we showed you how simple that function looks, right? That invariant function, it's very simple, and it is very simple. There is a bit of setup behind that. And if you want to learn all that setup, you can read my deep dives. You can have a look on the repo where this is all on my GitHub repo, the fuzzing repo. It's all there. But there's a setup, there's handlers, there's a bit of setup there. But with Satora, it's self-contained in a beautiful rule here, right? So with Satora, we've got two main ways to define what we would call invariants. We've got the rule keyword. The rule keyword, it lets us paint a picture to the prover, right? It lets us describe kind of a scenario. And then we use require statements to define relationships between objects or fields to constrain what the prover does with that. And the idea here is that we want to try and guide the prover to at least give us an initial valid state so that it doesn't break the invariant from an initial state that won't be valid. And the other way that we can do this is Satora has an invariant keyword, which you'll also see later as well. And typically an invariant is used for simpler properties that should hold true all the time, whereas the rule keyword in Satora is what I would use more often, and that's more useful for particular scenarios that we want to target. And what you can see in Satora as well is that it has what are called parametric rules, which is a very powerful construction here. So you can see in this comment, perform another arbitrary successful transaction F. And this is basically, it'll do anything just with these constraints. And that's a really cool, powerful parametric rule feature that lets you write very nice, concise Satora specifications. So Satora can solve this, the fuzzers can solve this. You know, we've got many good tools. It's just about using them and learning them and then using them effectively. And that's, you know, I'm a big believer in everyone upskilling, developers, auditors, sharing this information freely so that we can all upskill, we can all improve the security of our protocols. And by doing that, we can all improve the security of Web3. So I would highly encourage you to you know, learn whatever tool you're interested in. If you're interested in fuzzing, learn fuzzing. If you're interested in Satora, learn Satora. Learn whatever tool you're interested in, and then you might become interested in another tool, right? And it's just a matter of time. You can acquire all these skill sets and then put them to use and get better and better. And this will help our whole environment, our whole ecosystem will just become safer and more secure and more trusted and more respected. So now we're going to see how we go from a specification to an invariant. So here we've got a contract and our spec is simple, right? We've got a proposal and the proposal can be in two states. So either the proposal is active and the contract has ETH, or the proposal has been decided and ETH has been distributed or refunded, right? So we've got two states. We're either active or finished, essentially. Regular function plus end of life. And so we can make a very simple invariant from this, purely from the specification. Like, here is the magic. We don't need to read the code at all. We don't need to read, we just need a public API, basically, but we don't care about how this is implemented at all. And so what is our invariant? Well, it's very simple. We just check that if the proposal is in the active state, then it has a balance greater than 0, or if it's not active, then the balance is 0. And now you can see the code on the right-hand side and all the things that it does, but we don't care about that at all. You see how the invariant is not related to the code whatsoever. The code could be anything. We don't care at all. Now, this invariant is very, very simple, right? It's very simple, but it found a high severity finding where certain sequence of transactions could occur that would mean that funds would be permanently stuck in the contract, and it could be quite a significant number of funds based on how certain things went, right? And so this is purely a black box invariant. We don't care. We don't have to read the code at all. We don't care how the code is implemented. It's very simple. You can all write this. Anyone can write this. It's not complicated. It's not rocket science. You don't need a PhD. Anyone can literally do this, but it's also highly effective. You can find really high value findings like funds being permanently locked in a contract. Okay, here's another one. So on this one, what is our spec? So we've got a proposal. Oh no, here we've got the Satora. Okay, so here we've got on the right, we've got Satora. So this is the Satora solver. So you can see the fuzzers on the left, the fuzzing solution, and the Satora specification is on the right. And here we've used the invariant keyword for Satora. And again, it looks very similar to the fuzzer, but remember, there's no setup here. There's no handlers. There's none of the fuzzing infrastructure. It's just a beautiful, very elegant, very concise, self-contained specification that the prover can solve very quickly and effectively and find a valid way to break it as well. So I want you to see the power of both fuzzing and of Satora as well. And I want to encourage you to pursue whatever you're interested in, whichever tool is right for you, or perhaps both in time. But to really learn these tools and learn to apply them because they're very, very powerful. Here's the next one. So here we've got an NFT that is used in a DAO, and the NFTs, they have voting power, right? And the way that this works is that users, they have to deposit ETH collateral to back their NFT. Otherwise, the NFT will lose voting power over time, right? So the idea is if you want to have voting power in the DAO, then you've got to lock up your ETH so that you can maintain your voting power in the NFT. Now, there's a concept of a power calculation start timestamp, right? Before block timestamp reaches that start timestamp, the contract owner could create NFTs, and so they can create NFTs, they can hand them out, NFTs can be minted. And then once the power calculation starts, then for anyone who hasn't deposited ETH collateral to back their NFT, the NFTs will start to decrease in power over time, right? And the last property is that the NFTs, they all start with max power. And also, once the power decreases, you can never increase it again. You can only stop it from decreasing at whatever current level it is. So the idea is that if you want to participate in this DAO, well, you've got to lock up some ETH. You've got to have skin in the game, as we say. Alrighty. So do we care how this complicated logic is implemented at all? No. Do we need to read the code? No. We don't need to read the code. Auditors, they'll tell you, yeah, I read the code, read the code, read the code. I'm telling you, no, we don't need to read the code. We don't need to read the code. It's like magic. It's amazing, but we don't need to read the code. Purely from the spec, we can create some invariants. So let's think about the initialization phase of the life cycle, right? So when the block timestamp reaches the power calculation start timestamp at that specific block, all NFTs start with max power, right? Regardless of whether they have ETH backing or not. So what does that mean? It means that at that block, when the power calculation starts, the total max power in the system must equal the sum of all the created NFTs' individual power, right? So we can make very simple invariants here, right? We can have that at the beginning, at that block, that the voting NFT get total power does not equal to 0. And what I've actually done here when I did the fuzzer is I just hard-coded the block.timestamp in so that it gets set, and then the fuzzer just runs on that particular block to see if it can break it. And another one, so that total power shouldn't be equal to 0. So that would be, for example, if there was an attack where someone could somehow destroy all the power and set to 0. And the other invariant, which is that total power should equal to the init max NFT power, that's just a ghost variable. So in fuzzers, you'll define ghost variables and you'll populate them in your handlers. And so this ghost variable is just calculated when we do the setup by just calculating how many NFTs we have and then multiplying it by the max power per NFT. So these invariants are very, very simple, right? Very simple. We don't need to know, we don't need to read the code. We don't really care what the code does. We just purely from a spec have these invariants. But these variants were highly effective. They found a critical vulnerability where a permission, this was a beautiful exploit where a permissionless attacker could, at that exact block, at that single block when power calculation starts, a permissionless attacker could completely nuke the voting power of everyone's NFTs, send it all to zero, basically completely destroy the DAO. Beautiful, beautiful critical exploit, very beautiful, but found by very simple invariants, very simple and yet very effective invariants. And I want you to see how simple these invariants are, that anyone can do this. Literally anyone can do this. You just have to train yourself to think in this way. But that's a skill you can learn. But anyone can do this. Here's the next one. So here we've got a vesting contract that allocates points to users, which can be used to redeem tokens, right? Oh, and by the way, I didn't show you the Satora solution for that one because it's too big to put on the screen, but Satora can solve it as well. So this vesting contract, it allocates points to users, which can be used to redeem tokens, right? So you can think of, like vesting, like VCs and team members and stuff, investors that, the project goes live. They have to wait to get their tokens before they can, get some exit liquidity from retail. So anyway, yeah. So there's a vesting contract, right, that handles all this stuff, right? Now, I would highly recommend that if you want to do this stuff, that you would use Sablier, if I'm pronouncing that correctly. I think that's a really good platform to use. But if you want to roll it yourself, well, there might be some nice exploits for people to do. And we're going to see some of these here. So we've got a cheap invariant here, right? And that can be implemented directly into the code. And that's that at initialization, all points should be allocated. So we can see it on the right-hand side, the constructor here. We can see that we get an array of allocations, and then we go through them all. And then the last thing, that requires statement, total points is equal to total points, making sure that we've actually fully allocated the allocations, the point allocations. So that's cheap. We can implement it in the code. But the expensive invariant here is that for every single block that this contract executes until the end of time, until the end of Ethereum or whatever, right? As long as the EVM is running, this contract should always have this true property, which is that the sum of all user points always equals to the total points, right? So that there's no way for users to give themselves extra points, for example, or to change the total amount of points in the system. So that's a very useful property, but it's expensive to implement in the code itself because, like, imagine every time we perform any sort of operation, we would have to iterate somehow over every single point allocation, sum it all, and that would just be, you couldn't pay the gas on that. It'd be insane. So what we need to do is we have to implement this off-chain in our invariant fuzz testing suite to try to have some certainty that this is not possible. So again, do we need to know about all the different functions that this contract does with transferring points and calculating the vestings and all this stuff? Do we have to sit here and read all that code? No, no. In fact, we don't have to read any. We don't have to read any of it. We can have zero knowledge of how this contract does what it does. We do not care at all. At all. We do not need to read the code at all. Now, you should read the code, of course, as an auditor you will, but you don't have to, right? What do you need to do? Just define a simple invariant. Really, it's really simple, right? Look at this invariant, it's so simple. All we're saying is that the total points that each user has, when we sum them up, they should equal to the total points in the system. That is so simple. It is so simple, right? It's so simple, but this invariant found a high or even a critical vulnerability where someone that was entitled to point allocations could actually give themselves more points, and that would then let them drain all the tokens, right? That's an extremely valuable finding found by a very simple invariant that didn't even require you to actually read the code and learn how the system implemented its functionality. The only thing you had to do was just learn to think in this way and write the simple invariant. Here we got the same solution with Satora, and look at this beautiful Satora specification. Oh, look, it's so beautiful. It's so concise. How many lines is that? I don't know. Is it 10, 12 lines minus the comments? It's so beautiful using the rule construction, right? It is so beautiful, and it can solve this, find you a high value finding. It is very beautiful. I would highly encourage you to pay some attention and put in some effort and learn this beautiful solution in this skill. All right, on to the next one. So here we've got a token sale. So this is another DAO, and the DAO has some token sale functionality, and this lets the DAO to sell its governance token, right? So we're going to call that sell token. For another token, and we're going to call that buy token, right? So if you think of a DAO, you have to distribute the DAO's governance token, right? And you kind of want it to be sort of, perhaps widely distributed so that no one person can control the voting power. So one way to do that is to get people to buy their way in. So say if you want to have voting power in our DAO, well then you've got to buy your way in, right? So we'll mint you our DAO token out of thin air, and you can give us your hard-earned ETH or USDC. Sounds like a bargain, right? But hey, it's something that can be done. So one of the specifications of this token sale is that it's only for allowed users, right? So you've got to be on a whitelist or on an allowed list to be able to participate in this token sale. So that way we can control the distribution of the tokens, right? Because if anyone could buy it, then for example, anyone could control an infinite number of addresses. So then we can't control how many tokens one entity can get. And the other property is that each user can only buy up to a certain hard limit. Okay, and for simplicity, we'll just assume a one-to-one exchange rate. Of course, in the real example, in the real protocol that we audited, it wasn't one-to-one. But for our simplified example, we'll assume this. So we've got two invariants. Again, do we need to know how this token sale works? No. Do we have to read the code to figure out like how the swaps work and the buying and selling? No. No, we don't need any of that. We don't need to read the code at all, right? All we need to know is these simple properties and how to create invariants from them. So invariant number one is the number of tokens bought matches the number of tokens sold. That's so easy, right? Because it's one-to-one exchange rate. So that's now in the real invariant, you'd account for the exchange rate, but it's the principle. I'm trying to teach you the principles here. The principle is so simple. It's so simple. Anyone can do it, but it's so powerful. It's so powerful, right? And the second invariant is that each user can only buy up to the hard limit of tokens. Of course, it's so simple. It's so simple, right? It's not hard. Look at the implementations. Look at this code. It's like 5 lines, 6 lines. Like it's so simple. Yeah, there's some fuzzer, set up and handlers and stuff around it, some fuzzer infrastructure. But the invariant itself is so simple, right? It's not rocket science. You don't need a PhD. Like anyone can do this. Anyone can do this. Well, this invariant found a critical vulnerability where someone could actually buy tokens for free without paying for them, essentially. And there was another law vulnerability where someone could find they could get over the limit as well, so they could get more tokens than they were entitled to, right? So this stuff is like so simple. We don't need to read the code. We don't need to read the code, right? We just need to think in terms of invariance and have the skill set to write these simple invariants. And the fuzzer does it for us. It's like magic. The fuzzer does it for us. The fuzzer finds the exploits. It's magic. It's like magic. It's amazing. I don't understand why people don't do this. I mean, I can't make you do it. I can't make you do it, but I'm doing it. It works. Like it's amazing. It really is so simple and so powerful. All right, so we've seen some examples. I'm going to see some more, but we'll just take a brief moment to mention Chimera. So Chimera is a framework that's been developed by the guys from Recon, and it's a really useful library to use. So, one question that people ask me is, Dacian, which fuzzer should I use? And I would just say, use them all. Why just use one? Just use them all, right? And so you use Chimera for that, right? So the idea is Chimera, I just think of it as like a Swiss Army knife that has some helpful reusable libraries. And, you can just plug them in and use a certain pattern if you want. You can see my link there at the bottom of the deep dive, how I do it. And you can basically, use this library to write one set of code that you can use with all 3 fuzzers. And I think it's very cool. They've done a great job and I really like it. So I'd highly recommend you to check it out as well. And of course, if you use Chimera, then if you want to run your fuzzer in the cloud with Recon, then it's very easy as well. You can kind of just plug and play, and it's really cool as well. So, and I think Recon also have some cool tools that you can use, where they'll actually generate you the sort of the fuzzer infrastructure, kind of like for very easily and quickly as well. So there's a lot of advantages to using Chimera. I'd highly encourage you to check it out as well. All right, so now we're going to go through some more examples. In the workshop, these were as exercises, and I have to say, like, I'm really under the pump right now. So my slides, they're pretty rough. I've done some quick changes to them, but yeah, just bear with me. They're pretty rough. But so the first one here is vesting extended, and these are all real findings from my private audits at Cypher, right? So this is none of this stuff is CTFs. This is all real world findings. So here we've got a vesting extended contract, right? And this contract, it allocates points to users, which can be redeemed for tokens once the vesting period has expired. Okay, so we've seen that before, right? But this contract has an additional feature where users, they can also pre-claim a smaller amount of their total token allocation prior to the expiry of their vesting period, right? So, imagine you've got all these tokens, but they're vested for like 12 months, and you're like, man, I want to hit up that exit liquidity now. I can't wait 12 months. I need to sell, baby. I need to get exit liquidity, right? Well, you can pre-claim. You can pre-claim some tokens, and you can dump them on retail today, right? Okay, beautiful. So, what is the invariant here? Well, one invariant that already exists, which we saw before, is to verify that users can't artificially increase their points, right? So that the total points in the system have to remain equal to the total points when it was created, to stop a user from artificially increasing their points and draining the entire token supply, right? But there's an additional variant here, which is that users should not be able to pre-claim more than their total pre-claimable amount, right? So for example, if you can pre-claim 10% of your total amount, then if you can get around that, then you could pre-claim all your tokens very quickly and dump them all on the market very quickly, right? And that would let you get exit liquidity faster than other people, for example. So that would not be fair. So how can we solve this? Well, I've shown you, I've got here on the left is the fuzzer and on the right is the Satora. So the fuzzer, we've got two components here. We've got the handler, the pre-claim handler. And all that does is it just wraps the underlying pre-claim function of the vesting contract. And it just, it pranks our user. It gets a random user. And then it just updates total pre-claim. That's just a ghost variable that we use in the fuzzer to track the total pre-claimed in the system. And then the invariant, see how simple the invariant is, right? The invariant is so simple. The invariant is simply that the total pre-claimed in our ghost variable has to be smaller or equal to the max pre-claimable. And what is max pre-claimable? Max pre-claimable is just the total amount that all the users can pre-claim, right? So if a user can only pre-claim 10%, then we just calculate, when we start up our fuzzer, we just calculate how much each user can pre-claim and add it all up, and that's max pre-claimable, right? And so this invariant is very, very simple. It's very, very simple, but it found a very nice finding where a user could actually do some dodgy things to bypass the pre-claim limit, and they could actually effectively, pre-claim their entire token allocation before everyone else could, right? That's a pretty cool finding. It's very simple and very to find that. And here we've got on the right side, we've got a beautiful Satora spec. It's just so beautiful, so elegant. How many lines is this? 1, 2, 3, 4, 5, 6, 7. Eight lines of code. 8 lines of code. Can you write 8 lines of code? I can write 8 lines of code. Anyone can write 8 lines of code and find this vulnerability, right? It's so simple, right? We use the Satora, the rule keyword, and we just have some require statements to just have some basic sanity checks, right? To try and prevent the prover from starting from an invalid state. Because the way Satora works is, my understanding anyway, is that it does exercise your constructor, but then once the constructor has finished, it can havoc your storage. So it can set your storage to all sorts of crazy values that would never be actually valid. So you can use these require statements to define relationships between different objects, different storage elements, different environment parameters, to try and sort of constrain the havoc craziness that happens so that you can start from a valid state, right? But look, it's very, very simple, very, very simple here. And so either one of these could find this thing. It's not hard at all. It's very easy. You can do it. Anyone can do it. Okay, number 2 here. So here we've got an operator registry. So remember we talked about the types of advanced invariants, and one of them was where we have data structures that have interdata references. So that's where we have different mappings, different sets, whatever, and they have values that refer into the index of other data structures, and that there should be properties like uniqueness or connectedness between them, and we want to see if those hold up and if they're true. Well, here in this one, we've got this operator registry contract, right? And this just allows users to register as operators, and they get an operator ID. Beautiful. And users, they can also update their registered address. And so what do we need to do? We just have to write an invariant just to verify the integrity, right? The idea here is that an address can only have an operator ID. An operator ID can only belong to one address. There's a uniqueness invariant that has to apply. And so, before we go to the solution, do we need to know about all the implementation of how these things get changed and all the operations that can be done? No, we just need to know this basic property and be able to just code it up, right? So on the left, we've got the fuzzing solution. So here we just have a found addresses ghost variable. And we've got this property, this is our invariant function. And this just basically goes through the addresses that we found and then goes through the operators in the registry and just sort of adds them and compares them and sees if it's found a duplicate. Basically, that's kind of what it does. It's not that beautiful. It's actually quite crude, but it works. It does the job. But on the right, we've got another beautiful, elegant, concise Satora specification. Look at this. Look at this beauty. Look at this beauty. And remember that fuzzer has got setup. It's got handlers, setup, infrastructure, fuzzingcraft. This Satora solution. This is it. This is it. How many lines? We've got 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14 lines of code. Beautiful, beautiful, just beautiful, elegant, beautiful, lovely. But both of these can solve it. It's just a matter of which one you want to use. But I really like the Satora solution here. It's just so elegant, so concise, so beautiful. I love it. I love this stuff. Can you tell that I love this stuff? I absolutely love it. All right, another one, liquidate denial of service. So here we've got a liquidate DOS contract, right? And this allows users to enter different markets and have one open position in each market, right? So you can think of like some sort of a perpetuals protocol or some sort of trading protocol where there's heaps of different markets, and you can enter a market and you can have a position, you can be long or short in each market, right? And users, they can also be liquidated, right? So that if you're like, yeah man, I'm leveraging 100x long on Shiba Inu, right? And if the market goes against you, then you can be liquidated. Okay, so your mission, well, what we need to write an invariant here to verify that the liquidate function, it won't revert with any unexpected errors, right? Because we talked about denial of service invariance and how liquidation is a very core function of any sort of lending and borrowing protocol, because liquidation protects the protocol from incurring too much bad debt. So it's very important that we liquidate people as soon as possible. And so we only want liquidation to fail, for example, if the user is actually not subject to liquidation because they've got enough collateral, But we certainly, if the user is subject to liquidation, then we really don't want liquidation to fail, especially for crazy unexpected errors. Okay. So how can we implement DOS invariants? Well, there's a few different ways we can do it, but the most cross-platform way that I've seen is that we take the handler, this function handler liquidate, and we just wrap we use a try catch to wrap the underlying call to the underlying function. And then if the call is successful, if it got liquidated, then we update some ghost variables and do what we need to do. But if we did get an error, then we just create this array of the allowed errors. So this is actually a white box invariant because we have to go in to read the code just to see which errors are actually valid. So we put our valid errors here, and then we just call this is unexpected error function that just goes through and sees if it's an error that we expect or not, right? And if it's an error that we didn't expect, then we just have this Boolean that we set to true, and then we have that property, the function property at the top, that just checks that whether that Boolean has been set or not. So it's not very complicated. It is a little bit not that nice, but it is not very complicated at all, and you can certainly do this. And yeah, and this invariant found a critical vulnerability in a liquidate function where where a user could actually structure their trading positions, if you will, to actually make them impossible to liquidate, which is like really cool because then you could kind of do whatever craziness you want and you couldn't be liquidated, right? So that's a really cool, really critical vulnerability. But the invariant is actually very simple, right? We didn't have to read all about how the trading engine works and about how going long works, going short works. We didn't have to read all about how the liquidation logic works. We didn't have to do any of that. We just had to have this general idea, this general principle, and just go on and read the code to see which errors are allowed, basically, right? So again, it's very, very simple, very, very powerful, but very, very effective as well. Another one we've got, and this one as well. This one, unfortunately, at the moment, Satora, this is the one limitation of Satora, is that you actually can't get the reason for the revert. That's one thing that is not yet. It is apparently on their to-do list though. So apparently it's coming soon. So wait for it. I'm sure they're going to implement it because it's very useful. All right, so the next one is here, we've got a stability pool, right? So again, many sort of lending and borrowing protocols, they'll have a stability pool that can be used for various reasons to help the protocol remain stable under certain extreme circumstances. So here in this protocol, we've got a stability pool contract where users they can deposit a debt token, right? So that's the tokens that other users are borrowing, and and when they deposit a debt token, they receive a share of collateral token rewards from liquidators, right? So it's kind of like, you can stake your debt tokens, right? And then, that gives you some shares. And then when people get liquidated, the debt tokens get taken from the stability pool to plug the liquidation hole if there's bad debt. But then the collateral gets seized, and then the collateral gets distributed to the stability pool stakers or depositors based on their shares in the stability pool, right? Cool. So this contains like a lot of really complicated logic to calculate the rewards users should receive, right? So you can imagine, I'm sure that you've read some, you've seen some protocols where in the comments there's all this math, and then if you read the white paper, it's all like equations, and there's like these genius math PhD guys and stuff, right? Math PhD people, whatever. But the good news is that you don't need a math PhD to find a critical vulnerability in this contract, right? In fact, you really don't need to know any math at all, basically. It's so simple, right? You just have to learn to think in invariance. And then you can find a critical vulnerability in the math PhD code without a math PhD. It's like magic. It's amazing. It's amazing. So what do? Well, again, we just have this simple property that, hey, a stability pool should always remain solvent, right? Like there should always be enough collateral tokens in the stability pool to pay the amounts owed to the stability pool depositors, right? That's really, really simple. It's not complicated. It's not rocket science. You don't need a math PhD for that at all. What else don't we need? Well, we don't need to read the code, right? This is a black box invariant because it requires no knowledge of the complex reward calculations, the liquidation logic, the staking. We don't need to know any of that, right? We don't need to read the code at all. We don't need to know any of the implementation details. It's just a really simple black box invariant that literally anyone can implement and anyone can weaponize. Like these things I'm teaching, these are all weapons. These are literally weapons that you can pick up and you can put them into action. You can get amazing results, right? These are tools. They're weapons that you can use. And again, this exercise, it shows the one great benefit of invariant fuzzing. And that's that even without understanding any of the complex code, without a math PhD, without any of this stuff, you can write a simple invariant and the fuzzer can do the hard work for you. The fuzzer can find the critical export for you, but only if you provide it with the right invariant, only if you've learned to think in invariants. So what does it look like? Here it is. This is the invariant, right? How simple is this, right? It's a simple invariant that it just ensures that stability pool is solvent. So what do? We just go through every possible address. So we just have like a set of possible users, right? And we just go through them as in our ghost variable. And then we just, call up the public API to get the collateral tokens that they're owed, right? So basically we work out the total claimable rewards that the depositors are entitled to. And then we just check that against the balance of the stability pool, right? It's so simple. Like imagine just how simple this is. Like you don't need the math PhD. You don't even need to know how the code works. Like it's so simple. But this found a critical vulnerability in this protocol, a critical vulnerability where someone could actually drain all the collateral tokens from the stability pool. Right? It's so simple. It's so easy. It's like magic. It really is like magic. It really is just amazing. I can't express to you just how amazing this is and just how powerful this stuff is. How powerful it is. Like, I just love it, man. I love it. It is amazing. All right, the next one. We're getting towards the end here, so bear with me. So here we've got a collateral priority contract, right? So there's some lending and borrowing protocols. They're multi-collateral protocols. So the idea is that if you want to borrow, some let's say some stable coins or whatever, then you might deposit some wrapped BTC, you might deposit some wrapped ETH, you might deposit some staked ETH, whatever, right? You have a collateral basket, and then you can borrow against that collateral basket. Okay. Now, when this happens, there's usually going to be a priority order for liquidation. And the reason why that happens is because an important property of these systems is that post liquidation, the trader who got liquidated should be in a healthier state. And there's a few different ways to implement that. But one of the properties is that after liquidation, their remaining collateral basket should be more stable, right? So what does that mean? Well, it means that typically in these protocols, we want to liquidate the most volatile collateral first, right? So say for example, if you've got a collateral basket with like Shiba Inu and USDC, and you're going to get liquidated, then you want to liquidate the Shiba Inu first, and you want to keep as much of the USDC as possible because you have a more stable collateral basket, which means that you'll be less likely to be liquidated in the future. Whereas if you've got a collateral basket, if you liquidate the USDC first, and if your remaining collateral basket is just Shiba Inu, well, that's highly volatile. So you're actually more likely to be liquidated in the future. You've got a lower health score post liquidation. So we want to avoid that. Okay. Now, also collateral can be added or removed by the protocol admins. Okay. And so what do we want to do? Well, we just want to write an invariant to verify that the priority order is always maintained. And we've got two operations. We can add the collateral. When we add the collateral, it just goes to the back of the queue. And we can remove a collateral. The remove function just is meant to remove the collateral while preserving the order, right? So again, we actually don't need to know how those functions are actually implemented. We don't need to know really any of that. What do? Well, we just kind of define, the way I did it is I just defined a fuzzer with like four collaterals basically, and just kind of had like just the add and the remove handlers, and they just kind of hard code it. So like, hey, if it's at priority 0, then it goes to priority 1 when we add it, and same for remove. And so I'm just tracking the ghost variables. And then I have my property, the invariant here, where I just go through my 4 ghost variables and I just see if they match what's actually in the protocols queue, right? So it's just a bit of like drudgery sort of thing, but it's not hard at all. It's just, kind of just a bit of brute force, but it does the job. It's pretty simple. Here it is with Satora. Again, another just beautiful, elegant Satora specification using the rule construction. Just very, very beautiful, right? All self-contained. No setup, no handlers, no fuzzing infrastructure. Just beautiful. I just love it. It's just so beautiful. It's so elegant to me. It's fantastic. And this also solves it as well. So yeah, so both these things, they basically found a way that the collateral priority queue would actually get corrupted, so that when someone got liquidated, then the collateral priority queue would get corrupted, or when collateral was added or removed, particularly when it was removed, that collateral priority queue got corrupted, and therefore that would result in future liquidations in the wrong collateral being liquidated, such that when users got liquidated, they would actually end up with a less stable collateral basket, which would then make them more subject to liquidation in the future. So that's a very high value finding. It was a high validity. I think it's very legitimate. But it's found with very, very simple invariants, right? It's not, again, this is not rocket science. This is not math PhD stuff. This is just really simple stuff that you can do, that anyone can do if you just learn to think in invariants. And here we are, we're getting towards the end. This is a bonus one. So this is a function. The function is actually the underscore, rarely false. And that just takes 2 random uints. And it very rarely returns false, right? So this actually can't really be broken by the fuzzers, at least not that I've seen anyway at this point, because it's very rare for the fuzzer to stumble onto the particular number that will make it break, essentially, right? But can Satora break it? Yes, very quickly. And so what do we need to do? Well, Satora has an experimental plugin that lets you run Foundry tests, and it's really easy. This is it on the right-hand side. You just have this config, and then just one line, and then you just run the spec, and it'll break it like instantly. It's just really, really cool. So you can now run stateless fuzz tests using Satora, and so I would encourage you to check that out if that's something that you're interested in as well. And here's another bonus as well. This is from my current private engagement as well. This was you might have seen this on Twitter or X. So this is just stateless fuzzing. I haven't really covered it at all, but it is a very powerful tool to have in your toolbox as well. And so this is they have a sort of a vault contract, and they were wondering is our vault contract vulnerable to the first depositor attack? So one way is you could read the code, and maybe it is, maybe it's not, right? But another way, you just code up the fuzz test and let the fuzzer figure it out for you. And it turned out that, yeah, like we can just code up this really easy stateless fuzz test. It's very simple. It's very straightforward, right? We just run it through, got 2 users, give them some random assets, do a front run where the attacker front runs the first user, then transfers the tokens directly, and then the innocent user's deposit goes through, and then seeing if the attacker can then redeem, and then the invariant at the end that we want to verify is whether the attacker's total funds is greater than what they started with, essentially, right? So whether they can make a profit or not. And so this is what we want to do, right? It's very simple. It's very, very simple. It's not hard. So just, you can use fuzzing, stateless fuzzing, also invariant fuzzing, also form verification. It's a very powerful tool, and it's all about just learning to think, learning these thinking patterns. A lot of smart contract auditing is just learning how to think. Like if you see a finding that someone found in a competition or on Solidar or in a private audit, the good news is that you can actually find the same thing, and the only thing you have to do is just learn how that person thought that led them to the finding, right? So you can actually find anything that anyone else can find. But these tools, the fuzzing, the invariant fuzzing, the formal verification, these are very, very valuable tools. And the most valuable thing of all is learning to think in invariance. And oftentimes, for me, I actually, with some of these, I don't need to write the fuzzer because just purely because I've thought in terms of the invariant and I've read the code because I'm reading the code, then I can see how to break it straight away because I've trained my brain to think in this way, So, and you can get to that level. It's just a matter of practice and time, where at times you won't even need to write the fuzzer because you'll just think it straight away, and you'll, especially if you have some attacker mindset together with this, it's even more powerful, and you'll home in like a shark basically on it. So I think this is it. Yeah, this is it. So we've got a quote to wrap everything up from Patrick Collins. Make sure that your fuzz tests are good first. Highly recommend that developers should, as much as possible, implement fuzz testing prior to the external audit. I think that's very, very valuable both for the developers themselves as well as for the external auditors. I highly recommend that both developers and auditors learn to think in terms of invariance. And look, my goal here is to share my knowledge with all of you, developers and auditors, so that you can all implement this. Like it's really good to hear this and to see it and to feel good, but the key takeaway here is to learn this and to then go away and implement it. Implement it in your protocols as you're a developer, implement it in your audits as an auditor, and let us all level up together. Let us all increase the security and the safety of all our protocols in the space, so that we can have, as Patrick likes to say, we can deliver the Web3 that we promised you. So thank you so much for your time, and if anyone has any questions, we'll take questions now.
Amazing. Thank you so much, Dacian, for the incredible presentation. Maybe we can even have people raise their hands. We have 5 Q&A that weren't answered. The first one was from Chris Renzo. Any decent Sartorial tutorial or resource other than the official docs?
Yeah, so I actually used Cypher and Updraft's formal verification and assembly course. So that's a free course that you can see on Updraft. It is the most advanced course, but I think if you've been a developer and an auditor for a bit, you should be able to just go straight into it. And particularly, I think the second section of that course has many, many lessons on Satora. So I actually went and I've actually finished that entire course now, and that helped me a lot. Satora does have some gotchas, which can really it can really leave you sort of head scratching. Why is this happening? And so Patrick does cover some of those gotchas. So I thought that was very well done, and I benefited a lot from that one.
Amazing. If you can send me the link or paste it directly in the chat after for people to benefit, let's also share that. The next question is, were you using the Solidity fuzzing comparison repo when doing this presentation?
Yeah, so all the examples, I've put them in that repo. So you can go to that repo, my repo, the Solidity Fuzzing Challenge repo or something like that, and you can just get the repo, clone it, and it has all the in the source folder, there is all the simplified vulnerable contracts, and then in the test folders, there is all of the fuzzers, the Satora formal verification, everything is there. Yeah. And there's different ways you can use that. So what you can do, for example, is you could take uh, one of the vulnerable contracts and you could try yourself to create the fuzzer or the Satora specification. You could try and do it yourself. And then, if you get stuck, you can compare it to the solution that I've done. And that will probably give you the most benefit as well, because then you've kind of had a go, but you can also just go straight to the solutions as well. And so, I think that's a great resource that I've put together. And so you can see how the same vulnerability can be found with fuzzing or with formal verification.
Awesome. We have a question by Jason. He asks, CVL seems quite logical. Must it be common written for each invariant test, or are there some skeleton samples for types of tests?
That's a good question. Yeah, I would say so. Like everything, all the CVL that I wrote was from scratch. So it was sort of like custom for the particular invariant. I'm not sure if there's libraries of sort of common things. There could be, you know, how like with fuzzing, there's common invariants for like different, you know, ERC20, ERC4626, ERC721. There might be sort of you know, pre-packaged Satora specs for those things, but in terms of your own custom protocol that you're developing or auditing, you'd probably have to write, you know, a custom rule or an invariant, just like how you would for when you're fuzzing as well.
Great. So this is a bit of a difficult question, but in a multi-chain environment and rollups, state verification becomes more challenging. How would you extend invariant testing to verify consistencies across L1 and L2 states?
Yeah, I'll pass on that one. Maybe I'll let the other people answer that one. Today. I've tried to keep things very simple. So I've tried to give you as much value as possible that literally anyone can take and apply this. And I think I'll let the following speakers that they're going to discuss more advanced and even more complicated things. But for me, the big takeaway from my presentation is that this stuff is really simple and anyone can learn it, and you will get like 90% of the benefit from the simple stuff, and then maybe, you know, you'll get another 10-20% of the benefit from the complicated stuff. But I would say focus on the simple stuff first.
Amazing, honestly, great answer. And if I can shill my talk in 45 minutes, I'm gonna show a demo of how you could do it. Although Josselin will also give his answer, and hopefully Benjamin will also share his insights with the Uniswap v4. So let's go to the next question. Does the FV or Fuzz tool handle the 63 out of 64 gas rule? Is that something that you think you can find via your testing?
I don't know. Honestly, I don't know. Like I literally I spent about 7 days on learning Satora. So, and you know, people think, oh, CVL, Satora is so hard, formification is so hard. I literally went from zero to hero, and I'm not a hero. There's so much to learn, you know. But I went from zero to being able to write the Satora specifications to solve all these things in 7 days, right? So that's kind of goes to show you that like you can progress very quickly if you just have some time, have an internet connection, have a computing device, and you have the willpower to do it, right? Now, there's heaps of things that I don't know because I only put in 7 days, and this is one of them.
Yeah. Okay. Yeah, from my end, what I can say is if you change your handlers to purposely try to pass less gas, you can actually try a lot of stuff. So I believe fast testing can help you there, but definitely you have to put a bit of extra time. Let's see, the next question by Anthony is, how long did it take you to set up invariants and formal verification when you first started doing it? And how much value did you give back compared to now? Was it already super effective when you learned how to implement it? Well, I guess how long did it take you to get some results, Dacian?
Yeah, so the form of vocation, you know, like 7 days basically, right? Um, yeah, so you know, but I guess like yeah, 7 days of really sort of like serious, you know, digging in through, going through the updraft, you know, going through the and just a lot of trial and error. In terms of invariant testing, it's hard to quantify exactly how long. But I would say that, you know, the journey is part of the process. And one thing I would say is that, you know, like I try and not look at what other people are doing, you know, in life. Like there's always someone that's going to have a bigger house, a bigger car, a better watch. Like there's always someone that's better than you, basically, you know. So I just try and focus on myself and my skill set. And I wouldn't get discouraged if you think that you're not progressing as quickly as someone else. I would just focus on just executing and putting in serious time, serious effort, and you'll get there. You know, just anyone can do this stuff. Everyone, you know, the journey is important, but just know that, you know, everyone goes on their own journey, and we can all get to the destination, right? And it's, you know, some of us might get there quicker, some of us might get there later, but we can all get there. Like these skills, anyone can learn.
Amazing. Thank you so much for sharing, Deshan. And I've sent you a message as well. If you can share the links with me, I'll put them in the chat so they're pinned after so people can also check them out at their leisure. And with that said, we are effectively ready for our next talk. We'll basically start immediately, and we'll keep this format where we have Josselin now, then there will be me, then Daniel, then again me, and then Benjamin. So if we end up being early, we'll take a break. Otherwise, we'll just keep going. So in this case, we will just go for it. Prepare, because we have basically a treat. When I organized this event, I genuinely wanted to hear this talk, which was about contributing to Medusa. We have the engineering director at Trail of Bits, an individual that has been pioneering and teaching these techniques for over more than half of a decade through various workshops. He's behind the majority of the open source tools you use, such as Lidar and Echidna. And it's my great pleasure to introduce to you all Josselin with Submit Your First PR to Medusa.
Okay, hey everyone. First things first, I want to thank Alex and GetRecon for organizing this event. It's really cool to see kind of like the progress of fuzzing over time. And as Alex mentioned, we have been advocating for using fuzzing for quite some time now. And I'm really, really excited and happy to see more and more kind of like interest in that topic. But today's presentation is going to be about Medusa and how to make your first pull request. First things first, who am I? So my name is Josselin. I'm the engineering director of the blockchain team at Trail of Bits. If you don't know us, we are a security company where we specialize in high-end security technology. We work in the blockchain space, but we also work in traditional application security. We do cryptography, we do machine learning security, and so on. One thing that I think differs us from others is that we spend a lot of time focusing on research, and we always try to apply the latest kind of technique and the latest academic technique into our day-to-day application. And as a result, we have built many open source tools that you might know or might use, such as Slither, Echidna, or Medusa that we're going to see today. So today is about Medusa. I'm going to give a quick introduction into the tool. I'm going to give you some insight into what's a fuzzer, what are the different techniques, what are the different kind of categories of fuzzer. Then we will go a bit more into detail into how Medusa works and its fuzzing lifecycle. We will discuss a bit how to contribute to Medusa. And finally, I'm going to answer a couple of questions on a topic that I've seen people asking about, is why we are building a new fuzzer and what's kind of like the difference between Medusa and Echidna. So Medusa. Medusa is a smart contract fuzzer written in Go. It's based on Geth and it's open source. Basically, our idea here is to take all the lessons learned from Echidna, which is another smart contract fuzzer, and to apply everything we have learned through this new fundamental fuzzer. Medusa is meant to be really easy to use. So if you go on a new code base or on a new repo and you run Medusa init, it's basically just going to create a configuration file. You can see a snapshot of it on the right side, where there's just a couple of parameters that you can set depending on what you're trying to do. Then you just run Medusa fuzz, and Medusa is going to fuzz the project. On a really high level, how does it work? So you have a contract, which is in Solidity. You specify an invariant in Solidity, either through a function or through using assertion, the assert in Solidity. And Medusa is going to take this contract, is going to deploy it, it's going to generate random transaction to it, and its goal is going to break the invariant that you have specified. If we take a really simple contract, one of the most basic contracts you can think of, an ERC20 token. Let's say we have a transfer function, and in this transfer function, there is an obvious bug here where the developer used unchecked arithmetic to save gas. And what is happening here is that within the transfer function, the balance of the caller can trigger an underflow because there is no arithmetic check. And as a result, basically, of the underflow, if you transfer more token that you have in your balance, you end up with a really, really large balance. Nothing fancy here. This should hopefully not happen in real life, but it's just to give you an example of a buggy contract. Now, if we want to test that with Medusa, we need to define an invariant. And to kind of go back to what Dacian was saying about invariant, here you don't necessarily need to read the code, you don't necessarily to think about it, about like the code itself, but you can think about what should be like the expected behavior of the code. Here we have an ERC20 token. A simple property you can have is that no user should have a balance above the total supply. So let's say if you have an ERC20 token, you deploy with 10,000 token, no user should have more than 10,000 token. Well, pretty straightforward, otherwise something is wrong. If you run this with Medusa, and you call Medusa Fuzz, it's going to tell you it did manage to break this property so that no user should have more than 10,000 token by calling transfer and by transferring some token in the process. The thing which is interesting here is that here we were defining an invariant on the total supply of the token, and Medusa ended up finding a bug in the transfer function. So this is really like a really cool insight of fuzzing and property-based testing in general, is that you can find bugs in functions that you are not even looking for if you define your invariants, in a good way. So before going a bit more deeper into Medusa, I wanted to take a small step back and talk about fuzzing in general. So something I've noticed in the smart contract community is that for most of the people that have started their fuzzing journey through smart contract, they might not know about all the different kind of nuance and all the different kind of capability of fuzzing. So I just wanted to take a bit of step back and walk you through some of the high-level history of fuzzing. This is not going to be exhaustive. It's just in one slide just to give you some insight. In particular, if you start doing fuzzing on smart contract and then you want to move toward application security and like traditional application and do like general fuzzing, it is better to have some understanding of how we get there. So fuzzing started kind of a long time ago, around the 19 and the 18s. Basically, back then, the idea was really to do random input to a program. Miller in particular created, or not created, but like really pushed this technique where the idea was to take some of the Unix tools that you are using on a day-to-day basis and just feed them with random input. On the command line, or if they was using a file, just put some random input in the file and try to see if you could crash the program. And this was really, really effective. So back then, most of the language were considered nowadays like unsafe, like C and this type of things. And security was not necessarily a focus of the industry. So it was actually pretty easy to crash a program just by providing incorrect input to it. Around 2010s and kind of like the end of 2010s, a couple of new techniques kind of appear in the fuzzing world. We can think of grammar-based fuzzing, for example, with Spike and Pitch fuzzer. So here the idea is instead of having purely random input, if you know that your program is going to use some structure input, like for example, it's going to open a PDF, it's going to use an HTML file, you're going to have some kind of a structure into what you are looking for. You can define this structure through a grammar, and you can have the fuzzer fuzz the grammar. So this allows the fuzzer to, instead of just generating random data, to generate pseudo-structured data, which can be really useful if you are fuzzing protocol or this type of things. We have seen also during that same period an increase of mutation-based fuzzing. The idea here is that instead of generating purely randomly input to the program, you mutate existing input. By mutation, what I mean is that, for example, you might flip a byte within the input, you might change something really specific, you might do like an addition to the input if it's an arithmetic operation, and this is going just to give you a bit more kind of like a smart iteration over your input generation that just purely random. In 2013, there was a big breakthrough in the fuzzing ecosystem with AFL. Basically, like AFL, when it was kind of a release, ended up changing the game of fuzzing in that sense, because it was really, really effective. It was better than anything that was before. And for many years, it was basically the king of fuzzing. It reached that by a couple of really clever techniques. One of the things that AFL really pushed forward was this idea of coverage-guided fuzzing. So the idea is to have a feedback loop between the input generation, where you mutate some of the input, and the actual execution of the program. So what AFL was doing was that we're generating some input, you were executing the program, and you were keeping track of the coverage of what you have explored within this program, and you were providing this information through a genetic algorithm to the input generation, which was still mutation-based. And this feedback loop was really, really clever and efficient. I think back in 2014, the author of AFL made a blog post where he demonstrated that by creating a text file which was just having hello world inside and letting the runner fuzz for a couple of hours. The end result was a valid JPEG file. So that was really, really cool to see that just from a hello world, the input generation and like the coverage guided fuzzing ended up creating a valid JPEG file. So it was really like a nice advance within fuzzing. Today, coverage guided fuzzing is still kind of like the king for most of the general purpose fuzzer. You might find AFL++ or libfuzzer for like traditional application. It's also much more easier to integrate fuzzing in your day-to-day activities. There is a lot of inbuilt in language themselves, or there's a lot of framework around it. For example, cargo fuzz or test fuzz if you are fuzzing a Rust program, Atheris if you are fuzzing a Python application, or Go native fuzzing if you are fuzzing Go. So when you look at a fuzzer and you know how it works, you can ask yourself a couple of concepts and a couple of general questions that will help you to understand what type of fuzzer you are using or what type of fuzzer you need to build. The first question is going to be what is the target? So for example, if you're fuzzing a binary, you might not have access to everything, so you will be limited in what type of technique you can use. While if you have access to the source code, you will be able to just leverage additional technique. Maybe what you want to do is just to fuzz at the function level, which will also reduce the scope of what you're looking for. Then there is a question on how you want to generate input. Is this going to be purely random? Is this going to be based on mutation? Is this going to be based on a grammar? And so on. Then there is this notion of feedback loop that IFL introduced with the coverage guided. Even then, there is kind of some nuance into how you create your coverage. Can be based on instruction, can be based on branch, function, memory, and so on. If you think of smart contract, we could have a feedback loop, for example, on the gas consumption to try to generate transactions that use the most gas, if it's something you are looking for. Then there is a question of oracles. And this is kind of important because if you look at traditional fuzzer, up to like a couple of years ago, they were mostly looking for crash, for memory corruption. So they were just looking for a crash, or they were using a sanitizer, like address sanitizer, to detect this type of things. For smart contract, we are looking more at invariant because there is no memory corruption per se in the Solidity world. So what we are looking is to develop invariant. And this is really specific and different from traditional fuzzing. Looking for invariant is usually what we call property-based testing because we have a property or an invariant. Then there is also the question of what type of techniques are you going to combine your fuzzer with. You can combine it with static analysis, you can combine it with public execution, machine learning, and so on. There are a lot of kind of ways that you can combine the different techniques. For example, you can use static analysis to prune the program and only focus on specific function or specific part of the code. You can use symbolic execution and an SMT solver if you want to have an SMT solver solving some of the complex paths that you want to explore. Like, for example, if there's a complex condition that a fuzzer cannot kind of trigger due to its random nature, symbolic execution might help, and so on and so on. So Medusa, I'm on ask this question. It's based on source code. It's based on mutation testing, so it's going to use existing transaction and mutate them. It is going to be based on an instruction for the coverage in terms of feedback loop. It's going to use invariants, as I already mentioned, and we have a light combination with static analysis, but for now it's really lightweight. We basically extract the constant with static analysis and we provide that to the fuzzer. Okay. So how does it work on more concrete point of view? So when you run Medusa, the first things it's going to do is that it's going to generate a Genesis block, and it's going to deploy the initial contract that you want to deploy. This is within the configuration file under the fuzzing target contract. So it's basically all the contracts you want to deploy at first. If you want to deploy A, B, C, it's going to deploy A, then B, then C. Pretty straightforward. Then this is the initial deployment step. This is kind of like the first step before fuzzing. Once it has this initial step, it's going to actually fuzz the system. And to do that, it's going to create individual transaction, either completely randomly or using mutation using mutation on the code sequence from the corpus. I'm going to explain what's a corpus in a few slides, but basically it's a coverage information you are gathering when you're exploring the code base. Something to keep in mind here is that because you start from a genesis, you add transaction, up to some point, you need to reset the world at some point. If you don't do that, the exploration of the fuzzer might get stuck somewhere. For example, if you have a system with a token, the fuzzer might end up sending all the token to the address 0, and then they are just going to be stuck, and it doesn't make sense to continue to kind of fuzz and explore this world or this state just because it's going to be kind of not useful. So that's why in the configuration of Medusa, you have this fuzzing called sequence length, which is basically how many sequences do you need to do before resetting the world. The longer it is, the more complex you can have in terms of exploration, but the most likely you are also to explore non-interesting paths within the contract you are exploring. I mentioned this notion of corpus, so this is also something important if you start to contribute to Medusa or if you start using it. A corpus is basically the sequence of transactions that leads to increased coverage. And the notion of coverage here is important to understand because it might not be intuitive, but it's pretty standard in the fuzzing world. Basically, to track coverage, what we do is that we take all the instructions of a contract, we convert that into an array of bytes, and if the exploration through the call sequence hit one of these instructions, we just set the associated bytes to 1. So basically, we have an array with 1 or 0 to know if something was explored or not. This is pretty standard in fuzzing and in coverage-guided fuzzing. Based on that, we generate a corpus, which again is just a list of files with a sequence of transactions that leads to increase this coverage. So to summarize, basically, we have a genesis. We deploy the initial block, we deploy the initial contract, we generate or mutate inputs, we reset at some point when the call sequence length is reached, and we generate the corpus along the way that is going to help us to mutate new input or continue like the fuzzing in terms like many days, or like if you want to stop the fuzzer, restart, and so on. Okay. So we saw a couple of history of fuzzing. We saw a couple of like important step on how the fuzzer work. Let's talk about contributing to Medusa. Why I would advocate to contribute to Medusa? There is a couple of reasons for that. The first one, it's open source. And, like if within your career, you want to contribute back to the community, if you want to contribute back to the industry and help the industry to move forward, I think it's really powerful to contribute to open source security tool because they are going to help you to get there. They are going to help you to, basically help the industry to have robust practices, to have really good tooling, and to get to a place where we don't have that many incidents happening in the DeFi or even in the blockchain ecosystem. In addition to that, there is two things that are going to be, I think, really useful as a security researcher or as a software engineer. The first one, by contributing to Medusa, you will learn way more about fuzzing. Fuzzing is a complex technique. There is a lot of nuance to it. As I mentioned at the beginning when I was going through the history, there are a lot of different techniques, a lot of different kind of things to consider. And by contributing to a fuzzer, you are just going to learn this kind of fuzzing, all these different techniques, and you are going to build your own expertise. The more you know about fuzzing internal, the more you are going to be efficient to use fuzzing on a day-to-day kind of application where you will know a bit more about the limitation, you will know about the edge case, you will have like just a better understanding of the tool itself. Medusa is built on Geth, and this is really powerful in terms of kind of your own expertise standpoint because Geth is a de facto implementation in the Ethereum world. Many layer 2 and even some layer 1 are based on Geth. So by contributing to Medusa, what you are going to do, alongside is that you are going to build your own expertise on Geth internal, and this is just going to be useful in a lot of different situations. If you have to review a node, if you have to review like a layer 2, having this expertise of Geth is just going to help you, along the way. So generally speaking, contributing to open source security tool, I think is a really, really good way to fast forward, your career goals and to help you in your professional development. If you look for a job or if you look for, like a external contribution and things like that, having this expertise, having this demonstrated knowledge on a tool like Medusa will just help you a lot. So I highly recommend to use that as a motivation to contribute. So now if you want to contribute, It's pretty straightforward. You go on our GitHub, and I would recommend to start by looking for the good first issue and help haunted, because this is where you are going to really, start looking at the code base and not, be lost into like all the internal of it, and you can start making simple contribution. I have highlighted here 3 open issues that I believe are really, really simple to solve. Some of them are actually being opened by external contributor from TradeOffBit, which demonstrate that they have an impact because it's not just us that is interested by having this solved, but actually like our external user. So 3 examples here, that will help you to get a first good issue and to get like your first pull request accepted in Medusa. I recommend to start with something simple. I don't recommend to try to kind of contribute to complex code exploration, input generation, or like this type of things, because it's going to take you some time to get used to the code base. So start simple and see how the process goes for you. We have contributing guidelines. This is not going to be the most fun, but it is important, to follow them. Document the pull request, use the different linter that we provide. Basically, help us to help you to get the pull request merged. We want to have a high quality code base. So as a result, we do have like a small process with, a requirement in terms of documentation, requirement into linter. If basically if the CI is not passing, I would recommend you to go back and forth and try to fix the CI, because it's going to make it easier for us to merge the pull request. If you have any question, you can directly go into our Slack. In the blockchain channel, you will be able to ask any question to our developer team directly. Okay. One thing I want to also talk a bit about, in particular, if you're interested to contribute to Medusa, is why are we building it and why do we have a new fuzzer? You might be aware of Echidna, which was our first smart contract fuzzer. We have been developing it for 6 years now. It's in my opinion the first industry level smart contracts fuzzer, in the sense that this fuzzer has been used in many audits. We found countless number of bugs with it. It's really powerful. It has a lot of fine tuning. It is really kind of it has been built through the year based on our experience of doing audits. So why are we building a new further instead of just continue working on Echidna? Echidna has a couple of limitations, and the first one is it's written in Haskell, and Haskell is a really good language. It's a really cool language. I have a lot of kind of interesting concept there, but in practice it is hard to maintain and it is hard to contribute to. Not many people know how to develop in Haskell. Not many people are in the blockchain space. Finding people that can do Haskell and can work within the blockchain space is pretty limited. So I think Haskell is a good language, but for our use case, it is difficult, in terms of long-term sustainability for our fuzzer. We also have a dependency on HEVM. So HEVM is a virtual machine we are using in Echidna. It's a really cool project. They are doing an amazing job, and they have a lot of techniques and optimization within the VM. However, a couple of years ago, there was a couple of discussion about the maintainability and the sustainability of HEVM, and we had a bit of concern about HEVM being kind of still developed across the year. Turns out that they are still maintaining it and it's still going well, but at some point we had some concern, and this is when we started to look for an alternative virtual machine. So why Medusa? Echidna has a couple of limitations in terms of contribution, in terms of maintainability, and on a general standpoint, when you build a software like Echidna through the year, sometimes you make shortcuts. Sometimes you make decisions based on things you don't necessarily have the full context, because smart contract is constantly changing. So what we are doing is, by doing a rewrite in Go using Geth, we are basically using all the lessons learned from Echidna, putting them in Medusa in a way that it's just going to be beneficial for the community. We have also, because it's in Go, we have also a couple of end goals with Medusa that will not have been reachable with Echidna. For example, we are working toward having an extensive high-level testing API. The idea is that the user will be able to tweak some of the heuristic of the further per contract or more global. For example, you will be able to access a couple of hook systems within Medusa that will let you customize some specific execution, some specific kind of input generation, or whatever you want to do. So this is mostly because it's in Go, and it's going to be a bit more extensive than if it was in Haskell, basically. So for a conclusion, I would recommend you to take a look at Medusa if you're interested in fuzzing. We have in securecontract.com/Medusa documentation, tutorial, example on how to use it, how to set up, and so on. We have a tool which is called FuzzUtil, which has a couple of utilities. For example, you can easily take the corpus that Medusa is producing and generate from it from the unit test. This is really powerful when you do fuzzing and you want to convert kind of a file property into a unit test and debug it and provide it to the developer. What I would really recommend you to consider contributing to Medusa. And to do that, look for the good first issue help wanted on GitHub, pick one and try to solve it. Pick something really simple so that you can get started with that and get through it and see how you enjoy it. As a general also information, if you are building a protocol and you want help, for integrating the different further, for developing the invariant and understanding what are the invariant of your system, we have an invariant as a services where we help our clients, writing invariants, using the further, deploying the further in the cloud, deploying like the different setup. So if you need any help, please don't hesitate to reach out.
Amazing.
Let me see if there is.
Yeah, thank you very much, Josselin. Yeah, we're going to read out the questions from the Q&A. If you have more, feel free to add. The first one is from an anonymous attendee, and it asks, if you can only choose one of the two due to time budget constraints, in which cases would you recommend fuzzing, and in which case would you recommend formal verification?
So that's a really good question. We actually have a blog post about that with fuzzing versus formal verification. From my experience, fuzzing is just faster and easier to use. Formal verification is a really cool and powerful tool. However, if you have if you have to pick one, start with fuzzing. I don't think it makes sense to do formal verification if you haven't started with fuzzing first, just because kind of like the amount of return value you will get with a fuzzer is just higher versus formal verification for a dedicated amount of time. Formal verification is really useful if you have specific piece of code for which you want higher guarantee, like for example, if you have complex arithmetic or specific, assembly usage, and you want to compare with a non-assembly version, for example, formal verification will help you. But if you have limited time, start with fuzzing. It's just much easier.
So the next question is a bit technical, but basically they show you this code with two arrays of uints where you have to specify a length, and basically the length of both inputs must match. And the question is, will the fuzz or FV cover these cases of low-level manipulation, like memory pointers? Do you think fuzz over FV? What do you think of fuzz over FV in this case?
Okay, so for the people that don't see the chat, basically, the question is about a function which use an array and the array as a specific length. And the question is, can further or formal verification handling like kind of a parameter where the input is an array with complex lengths? Short answer is it depends. For formal verification, it depends on the assumption they're going to make on the length of the parameter. For Certora, I would assume there is a parameter to do that, but I haven't used Certora in a while, so might be wrong here. For fuzzing, because it's based on random generation, it might or might not work. You can, like, for example, if you know you have complex setup, you can also help the fuzzer to get to that point. Like, for example, if you know you have specific array manipulation with specific length, you can create like a specific harness that are going to make the fuzzer just faster. Fuzzing is based on random and statistic approach, so there is some risk that it might be more difficult for this type of case. But I would have to try it.
Fair. So the last question we have is, before contributing, what will be the best way to even start fuzzing with Medusa? As in example vulnerability contracts, then we run Medusa and understand how they work, DVDFi, Ethernaut, or something else maybe? What would you recommend?
So on this slide, the second link, securecontract.com/Medusa, you will find documentation, you will find tutorial. We have also a bunch of exercises that were created for Echidna in the Echidna section that also work with Medusa. So I would recommend to start with that. Go on the exercise 1, 2, 3, 4, 5, and just get a sense for how to use a different tool. Start simple, never try, once we are done with exercise, never try to write complex invariant at the beginning. Start with the most simple invariant you can think of. if in a process of writing an invariant for a code base, you find a bug right away, it's probably a really bad indication. Either the code base is in a really poor state, or you are, trying to find something much too complex at the beginning. When we have a fuzzing engagement, we always start with something simple and we iterate over it.
Amazing. Thank you very much, Josselin, for the presentation. Thank you for organizing and also for the open source work you've done. I hope we get a ton of new Medusa contributors. Because of timing reasons, we're going to get into our next talk, which I'm going to be doing. So I'm going to start sharing my screen and I'm going to jump right into it. And then after me, we're going to have Daniel from Origin Protocol. And I'll make sure to introduce him properly. Then this talk instead is called A Glimpse into the Future of Invariant Testing. And it's effectively something that we had to work for about a year to get to while building on top of open source stuff. So hopefully this tickles your imagination as we go through the past, the present, and possibly the future of what invariant testing can look like. So in terms of who I am, the co-founder of Recon, arguably between the top 30 or top 50 solo researchers in the world currently. And I work with Spearbit and Codarena as a security researcher. And previously I was a builder for Badger, where my contracts have handled hundreds of millions of dollars. And this year, by founding Recon with Antonio Vigiano, we work with Centrifuge, Badger, Corn, and more recently Liquidity, as well as Balancer DAO. And the reason why I started Recon was I thought you could just, fuzz some sort of some sort of a smart contract to see if you could extract some value. And this is actually something I had built and I showed it around back in March of last year. And my idea was, you could have some sort of a CI/CD and perhaps put some solidity magic and, magically this will work. And then I met Antonio in Paris at DeFi Security Summit. And fundamentally, he was working on standardizing effectively the interface for how to write fuzz tests. And that was done through the Chimera framework, which effectively makes it so that you're effectively writing Foundry tests, and then these Foundry tests can be tested via Echidna, Medusa, and more recently even Control and Halmos. And so that's kind of what we built. We built a way to run this in the cloud. This is what our Pro panel looks like for Recon Pro. We fundamentally are running Echidna. As soon as we break a property, we show you the broken property and the repro. We have compressed logs. We have the ability to share a job, and we automatically also generate a markdown report. And currently we support Medusa, Echidna, Foundry, Almos, and Control, although our workflow is mostly focused on Medusa and Echidna, because anytime we break a property with them, we are able to generate a Foundry repro that makes it so that even if most of your team's developer are not familiar with this tool, as long as you are familiar with them, you can just give them the Foundry repro, and then they can investigate some sort of a root cause. And hopefully, if you go around some projects like Corn and Liquidity, you're gonna find our runner running on their GitHub as CI/CD. And anytime one of the runs is done, we basically give them this report with any broken property. And again, any broken property will have a Foundry repro so that you don't need to run Echidna and Medusa, even though that's what we're doing because they're amazing tools. But we can give you send you back to Foundry, which tends to be easy. And so if I were to show you the 5-second demo of how this works, we literally just log in on Recon. And then I will go on any repo that is compatible. For example, our Create Chimera app is compatible with Recon by default. And then all I have to do is just paste the URL, and I'm basically able to run this job. And then within a few minutes, you're going to see the output here. So something I can do just for the sake of demo will be to share the URL, and then I can paste it here in the chat. So you basically can see it work as I'm doing the presentation. But this is basically the current state of our tool. We can offer it instantly to any project. It's not new tech. And it really comes from the insight that Antonio, in a sense, had last year that most people would rather have a more powerful foundry, more so than invest a lot of time with a different language. This is something that one day we'll perhaps talk deeper about. But most people understand Foundry. They already are going to write Foundry. So for them, if we can make it better and make it faster and make it run other stuff, it just gives them more power. And so it seems like a pretty clear direction that we're currently seeing in the present. Whereas what I want to show you in this presentation is more about the future. And so my guess for the future is that invariant testing is a form of due diligence. It's a form of automated testing that ensures that the quality of your due diligence is consistent. Obviously, it's not a silver bullet. You only can detect and prevent whatever you tested for. But this simply means that as long as you have the suite and you're willing to rerun it, you can never miss the same bug. And that's what we really see with more professionals. They typically will maintain their suite, then perhaps they do an audit, and then any mistake they make or any bug that goes through that is found via manual review, then they will update their suite to detect. Another more advanced or niche use case we're seeing is the idea of simply having constants in your tester. You can see here, this is the PSM3 by Spark. This is Angstrom by Sorella Labs. This is the centrifuge repo, and this is an Euler tester. But fundamentally, many tests, they tend to have hard-coded constants, whether it's because you're testing against a mainnet target, or whether because you have some sort of a precision value, or perhaps you are coding the decimals for the tokens that you want to test for. And so something we've introduced is a tool or a feature called dynamic replacement, which means that we can simply grab a constant from your test, and then we just go in the UI, you will type the variable name, the interface, and the value. So you will type WBTC decimals of uint8 with a value, for example, of 18. And in doing so, you will produce this JSON data that allows our tool to rerun your test with this change constant. And so the key idea is that instead of having to maintain multiple branches just to run a variation on your test, we can simply reuse the corpus, we can simply use the config, and we just change a constant for you before running the tool. And this is just the most basic way to use this tool, because another thing we've been doing, especially with Badger this year, is simply to rerun their fork suite multiple times per day as a means to make sure that no new property is broken. So in the case of Badger, they had specified a precision threshold for some of their rounding errors. And so by rerunning the suite, we are able to predict whether these possible rounding errors will manifest in prod. And so this is something that we're seeing is you can use the invariant testing as a monitoring solution. However, the problem we've had with our previous iteration was that we will simply run it on a schedule instead of running it when it matters. And so that's what we wanted to address. And this is an example of how you will set up fork testing with Create Chimera app, which is a free template anybody can use. You will literally just set up your suite. Then you will add a couple of extra functions called setup fork and perhaps setup actor forks, where you effectively do these two things. You set new addresses, and also you roll and warp to your specific target. And then through our UI, we have a feature called dynamic block replacement that makes it so that we can grab the latest block from the RPC, and then we can dynamically replace the block number and the block timestamp in your tester. Meaning that, let's say Badger, they have a job running every hour. They don't have to update their GitHub every hour. We just dynamically replace those values, so we're testing against the latest block. And this, in combination with alerts, makes it so that if a property were to be broken, hopefully that never happens, but if a property were to be broken, we will be able to alert them through most likely PagerDuty in their case. But we fundamentally have this integration that allow us to be warned anytime a future state transition could break one of these invariants. And so mixing these three ideas, I really want to introduce to what I think is the future of invariant testing, which we call governance fuzzing. So the idea is that we have dynamic replacement of governance values. We're going to have fork testing, meaning we're testing against deployed targets, and we're going to alert you on any broken property. And so the key idea is that anytime you have an action queued, whether it's your safe, your time block, an event, or your governance contracts, we're simply able to listen to them through a very simple event listener. We can then set up a job on Recon, and then fundamentally we can rerun your invariant tests with the new parameters, meaning that we can predict, simply by trying, we can predict whether those changes will potentially cause an exploit or potentially cause a property to be broken. The most common example, which you can see here in code, will be a multisig. We can basically listen to the call scheduled event for the target, the value, and the data. And then as long as you set up your invariant tester to have these constants, we can then dynamically replace them into a function called, in this case, do.gov fuzzing, which makes it so that this function will be included in your test. And as such, if this function is necessary in order to break any property, it will appear off of the logs. Another use case is custom governance contracts. This is the Liquidity governor. It emits an event called register initiative. I've worked with Liquidity under v2gov, and so we're open sourcing today this repo that automatically does this. And the idea is literally we're going to warp and roll to the specific time and block at which an initiative is deployed. And then we dynamically replace the address so that we can verify whether an initiative will throw, whether an initiative will require more gas than intended. And so it's definitely not a silver bullet, but this means that we can offer a team like Liquidity the ability to perform due diligence in real time on any new initiative that is deployed and to share that testing with everybody. Another example will be cross-chain messaging. This is something we'll most likely open source in the future, but we simply can listen to the packet sent event, meaning that by doing that, we can then construct a payload for an invariant test that tests for this type of messaging, and then we can simulate whether this state transition will break any specific property. And the use case that I'm going to demo now is listening to a factory. So this is something that I demoed to the Euler team. So, you know, it's not, it's a demo I built for them to show them at DevCon. And fundamentally, the idea is that we can listen to their factory once a vault is deployed, and then we can automatically run invariant tests to check whether the configuration will cause to break some properties. And so I'm going to show you this demo right now. Basically, I have this fork tester called Euler fork, where effectively I have a setup for the specific this random block and this random timestamp, and all of my constants are set to 0. And then I'm here on Sepoli. I basically have a deployer that will call the factory, and it will effectively trigger a deployment. And so we have a server effectively listening to this event. And what's going to happen is we're going to create what is called an event-driven job. You can see an example here where the event-driven job will have these parameters that come off of the event on chain, meaning that we're able to test exactly for the new vault that is going to be deployed. So I'm going to hopefully get that to work right now. I have just some test Sepolia stuff here. And let's see if we have enough gas to pay. Hopefully it makes it. We'll give it a minute or so. But fundamentally, what's going to happen is my account is going to call the factory. The factory is going to deploy a new vault. And then the new vault will trigger a job with all of these parameters being picked up from the various events that happened on chain. And then what's going to happen to the specific tester that you can see here, the example, is the original code looks like this, new vault, IE vault address 0, whereas the tester one will basically have the specific addresses, meaning that the key idea is your engineer spent possibly even 6 figures writing these tests. And so what we can do is we can quickly repurpose them to automatically perform this type of due diligence. So you can see here that the transaction went through and that my event-driven job is scheduled on Recon. And so all I have to do now is, for example, share it with you guys, and you can check this live demo as it happens. And if you think this is cool, hopefully you, first of all, try it for your own projects. And instead, if you want to do it and set up this type of monitoring at a professional level, you can also come talk to us. We should be able to repurpose most invariant suite in an hour, and then some suite would take about a day to repurpose to be fork testing compatible. But once that work is done, and obviously the real work was writing the invariant test, once the work is done, it's actually fairly easy to convert them into monitoring. And I believe this is the best way to do monitoring because it's specified by your best engineers. And as such, it should help you prevent any possible issue. And so I hope this inspires you to push with invariant testing. And I hope this becomes a best practice that hopefully prevents reintroducing any possible bug simply by raising the bar and making sure that we are always testing to the best of our ability. So yeah, that was my presentation, a glimpse into the future. Thank you all for checking it out. The next presentation is going to be by Daniel. Give me a second for the screen. So our next presentation is going to be by Danielvf. He has built 3 protocols up to 9 figures. He's currently working at Origin. You probably know him from some of his Twitter breakdown. And this talk is called You Should Probably Be Fuzzing. So give a warm welcome to Daniel.
Okay, cool. Then I'll get started. You've already had an introduction to me. And what I'm really passionate about is not getting hacked and studying how a protocol can not get hacked and build things securely. So this talk is not about how to fuzz. I will try to not say anything there, or about doing specific things. This is about where fuzzing fits into the mix of other ways to secure protocols and kind of its strengths and weaknesses. So what are we trying to do here? Well, this is the simple answer. We're trying to move from unsecure to secure. You want to launch code that's not going to get hacked. And the reality, though, is you can't actually do this because that's not actually how the world works. There's not a Boolean between secure and non-secure that suddenly gets flipped, at least as far as you can really know from most things. So to quote a wise man, security is a gradient. This is from Storm Blessed of Urine. And so a much better way of thinking about it is you're trying to move from having a lot of bugs and push up to having no bugs. And you're never quite sure if you've absolutely gotten there. But you're trying to do this. And an even more accurate chart of this looks like this, where you have something where the more and more and more and more you put into something, the fewer and fewer and fewer bugs you have. And there's a decreasing cost-benefit ratio as you go up this. So as a protocol, you're trying to work this curve as efficiently as possible to get up it as high as you possibly can for a given amount of money. And you're also trying to figure out where you are on this curve currently and where you actually need to end up given the goals of the project and the funds that will be in the project. And you have a lot of tools that are available to help you do this. So starting from kind of the bottom up, you've got the architecture design of your code, the actual writing of your code, unit tests, static analysis like Slither, internal code reviews, fuzzing, which is what we're talking about today, external audits, formal verification, code contests, bug bounties, your operations skills, your monitoring setup, your incident response skills and stuff. And so how does fuzzing fit into this? Should you be using it or not? One interesting thing, looking back at this curve, is that it's not like these things are always going to give you the same benefit for every project. The projects are actually different, and these different tools have different abilities to catch certain kinds of bugs. So jumping to the really old StarCraft, different units have different counters, and different bugs have different counters. And so tools that are good for some kinds of bugs are not as good for other kind of bugs. So we're going to talk a little bit about where fuzzing fits into that. So again, cost, benefits, weaknesses, and strengths on fuzzing. All right, what is fuzzing? Well, you guys have just been here for 2 hours listening to people talk about fuzzing and what is fuzzing. And so I'm going to be really, 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 really short on this. And let's just have this to hang a hat on. Fuzzing is doing random actions, or what could be thought of as random actions, and then checking that something bad has not happened and repeat that. And this is just a framework for thinking of how this fits into, because this really tells us where fuzzing is useful and where fuzzing isn't. One big powerful thing is that, in my opinion, fuzzing is much better than unit tests at finding bugs. And unit tests are essentially at this point industry standard. If somebody does not write unit tests for their code, they're probably doing something really bad. But unit tests only catch the problems you imagine and the paths that you imagine. And this is where fuzzing is really better, in that you can define a problem, and you still have to define the problem, but then the fuzzing finds the path to making that problem happen. Can a mortal fuzz? In the past, fuzzing has been extremely difficult to do. Only a rare handfuls of wizards could actually get useful work done. The tools were a bit archaic, even hard to get set up. You had to invest a big chunk of time figuring out how to even get started. But I think this is an accurate depiction of the current state of fuzzing. Before this year, it was extremely difficult. You had to have genius level people, or people who devoted their careers to fuzzing. And then I think in the future, if you're not writing fuzzing tests for a lot of situations, or then you're probably doing it wrong. We are at the breaking point where the tools have caught up, or that the tools have crossed the threshold where there are usable tools, good tools, and a lot of people on this call have made that happen. There's kind of been three things that have intersected. From my point of view, one, we've seen a whole lot of usability focus on making tests easier to write from the Foundry side of things, and DApp tools, where that came from. And then we've seen the fuzzers get tremendously better at a lot of features that make things much easier to write tests with, getting more usable, easier to install. And we've seen people doing fuzzing, kind of bridging the gap between providing feedback on how to make fuzzers easy to use. So at this point, there are multiple good open source engines, and you can actually get a lot of tests to run in multiple engines with write once, run in multiple engines. If done right, you can write your fuzzing invariants and stuff almost in a sense that are like tests. There's now things like vm.prank that are in fuzzers now, so it's much easier to reason about who's calling what, as well as a constant flow of cheat codes to make fuzzing more like unit testing. And when you compare it to formal verification, fuzzing is imperative. That random series of actions is a series of concrete actions that have happened. And when you're writing code to make things happen, again, you're just writing code that runs as if it was running in time. There's a lot of deep magic behind the scenes in fuzzing, but from a thinking about it point of view, you can just think of it as some imperative process, or the output is some imperative process, and that's also sort of how you can write your checks and stuff. So this makes it quite easy, I guess, once you get used to it, but to run. So skill still matters, though. Fuzzing is not at the point, and maybe it'll never be, where anyone fuzzes with no thinking at all. There is quite a difference between myself writing fuzzing tests and somebody who's an expert and a master at it. And so depending on your project, you may want to bring somebody in to do fuzzing, or you may want to write stuff yourself. But skill still matters. Skill matters in writing unit tests too. And what we've seen is that the skill curve in that has come way down to the point that it's expected that anybody will be able to do that. And where we are currently with fuzzing is that you can get a tremendous amount of benefit as a protocol by writing your own fuzzing stuff and running that in with your unit test, and then evaluating if you need to take that to the next level. All right, let's talk about kind of the meat of this, which is this a good fit to fuzz? One of the big things is the state complexity possibilities. It used to be that it was only worthwhile to fuzz things that were just on the right side of the yes fuzz set here. If something is really, really simple, there's probably not much benefit to fuzzing it. And if something is insanely complicated, then you probably need a super expert to work with it. But if you've got dozens or possible states or something that something can be in, then fuzzing is a fantastic thing for this. We just finished writing something that's basically, in my opinion, kind of like the perfect fit for fuzzing, where we have a contract that has 4 different account types. These account types can change one into another, and each one has different accounting systems behind the scenes, and these account types can interact with each other and send money back and forth. So that's a real pain to test from a manual testing point of view, because you have basically 16 different possible interactions between them, and then you have all the different ways that they could change from one into another, or the things that they could do. You have to test each thing that can be done and verify that it works in each of the 4 different account types. Real pain for unit test, but is super easy for fuzzing. And yet at the same time, the number of different states is not so high that randomly trying things is going to miss stuff. There's a similar diagram on code complexity, but it's not really going to be helpful here. So one of the weaknesses of fuzzing is integrations. If you're integrated into another protocol, in order to actually test your system, you would need to test essentially the entire other system as well. And that's something that's going to be a tremendous cost to do, and probably not worth doing, because you're basically replicating their system in order to function effectively. So often, if you have boundaries between things that are your own code and state, and that you may want to fuzz, and then if you have a separate contract that's an integration into a third party set of contracts, that may not be such a good solution place for fuzzing. If you have dumb pipes that just move basic amounts of money from one place to another place, that again may not be a efficient place to fuzz, and that kind of actually ties into the integrations as well. Things with state is a perfect thing to fuzz, because fuzzing can do the state transitions for you kind of automatically, and be checking it at each possible way that things are still correct. And that even gives you a further benefit, that your system might allow some state transitions that you didn't even think were actually possible, but your code allowed them. Things with state that interact with things with state, same thing. Good candidate for fuzzing. All right, so you can kind of summarize it back to just looking at what fuzzing is: random actions and checking that something bad has not happened. And that's kind of your guide stick for should I fuzz or should I not? Is this going to be something that's going to find the bugs that you're looking for, or is this not going to find the bugs you're looking for? All right, so actually using fuzzing here. I was an early user of formal verification, and even though that has some difficulties, just the thinking in terms of invariants has changed how I code review, how I write code. It is incredibly powerful. So even if you just try fuzzing and don't actually even end up using it, if you just start thinking in terms of what are things that should never happen, or what are things that must always happen, how are these two things, should these two things always be related, it will massively improve your ability to read code and to write code. And this is a core of fuzzing. You know, half of fuzzing is checking that something bad has not happened, which is the invariance. Fuzzing works great early in the process, or maybe early mid in the process. Your code should be written. You should have your API that you're roughly going to be using. But at that point, the same point you would want to write your unit test, is great to have your fuzzing test in, even when the code is not perfect, because the fuzz tests that you write carry over and keep running. And so you can keep running them at every change in code you make as you go through doing your improvements, tightening your code down, simplifying things. And it will let you know as soon as you've made a mistake. And this really speeds up the second part of your development. When you get a report in from your audit and they say, change this piece of code, and you make that change, your fuzzing test runs and keeps that entire investment you made in creating them, and then tells you, oh, the auditor missed something and told you to do something stupid, and this actually introduces a bug. So it's basically like free audits at every commit, at every part of your process during future upgrades and stuff. The tools are now ready. We have crossed the line, as I said earlier, to the point that the tools are just ready. I don't know that there's the world's best guide yet, and forgive me if somebody's gone earlier and said this, but I don't know that I could just point somebody and say, this is how you fuzz yet. But the tools are there. So in the next, next year, in 2025, should be the era of teaching people how to fuzz so that they can use these now and widely put these into protocols. So the title of this was, you should probably be fuzzing. But I want to emphasize the you here now. You should probably be fuzzing. There's probably some part of what you're doing that fuzzing would make better. And so give it a shot. That's it. Any questions?
Thank you, Daniel, for the presentation. We do have a couple of questions. Josselin flagged himself, but let's have you also give it a shot as well. So he says, we have Gurkirat. He says, I'm currently watching the Trilobits Echidna series on YouTube. Once I finish that, can I move on to Medusa, or is there a steep learning curve for Medusa? If there is, could you suggest additional learning resources for Medusa beside the official documentation?
Yes, so I'll say my piece real fast and then go on to Josselin. In my opinion, Medusa is easier to use than Echidna by quite a bit. So if you learn how to use Echidna, you should have no problem moving to Medusa. Josselin, do you want to answer?
Yeah, exactly. If you know how to use Echidna, Medusa is pretty easy.
Yeah, I completely agree. And in the next talk, I'll quickly talk about why neither of them are perfect, but they're definitely way easier to get started. It's 5 seconds and you should be good to go with Medusa. It's amazing. The next question is by Jason. He says, does fuzzing generate possible invariants to test? I ask because it seems like compared to fuzzing, invariant testing is only as good as the cases you can think of, just like unit tests.
Yes, and this is something that's just as true with formal verification as well. And it is only as good as your invariants are. But you have to think of much fewer invariants with fuzzing than with unit tests. So you can put more thought into it. Like maybe 20 invariants may get you be everything you need for a protocol or something to really hit the core of the things that are going to matter. So yes, you have to get the invariants right, and you've got to be very careful that you don't put something in the invariant that skips, makes the check worthless. Like if you're only checking it in a certain situation, and then that situation turns out to be you wrote a sign wrong or something, and suddenly this invariant always records as true or something. So yes, invariants matter. Invariants are tricky. They are much less tricky, I think, in fuzzing for some reason than in formal verification. One, you're writing something much closer to how you would write a unit test. And two, again, that just imperative nature makes it much easier than, in my opinion, writing the same invariants in formal verification. Now, maybe that will change, and hopefully formal verification also moves up to the point that mortals can use it.
Amazing. We have my upcoming talk, Echidna made me do it. and then stick around for the main event from Benjamin. But before we do that, I thought we could literally improvise for literally 3 minutes. Would you guys want to add something else around the idea of, I guess learning to fuzz or even just, I guess some of the gotchas there. I guess, would you want to expand further on this Q&A?
Well, just as important as in writing invariants is also making sure that all the actions get called. So if your system is complex, it can be easy to fuzz things that aren't to miss areas of your protocol with the fuzzing. That's a much more advanced topic. Again, I think just getting started and playing with it is a fantastic thing, and will get you a certain amount of benefit even without being an entire expert. I wouldn't, if you're not a super expert and you don't know where the pits are, you can't rely on it as, oh, I fuzzed this so there are no bugs. There's still bugs will probably have slipped through, but you probably will have found some things that were wrong. Josselin, do you want to add anything?
Yeah, sorry, I was answering the chat, so I think I missed part of it.
No problem. Alex, you?
Yeah, I mean, from my end, it feels like fuzzing is literally all about the coverage report. Fundamentally, if our tools were so advanced that we could just write the properties, I think fuzzing will be the industry standard. Some people will even argue about not even writing unit tests. But the issue with, so far at least, is that the scaffolding, the setup, reaching good coverage tends to be the majority of the work. And then even the way in which you reach coverage ends up informing or possibly even changing the way you can write your tests. A classic example is once you check for specific roles, you either have very nuanced properties, or the fuzzer will always just find a way to, rug itself and then basically break your property. So problem. And yeah, from my experience, the best thing is to give it a shot. And what I'm telling all my current invariance engineer, people I'm training to do this professionally, is try to write the least amount of code and keep it as simple as possible, because it's already, it's already a mess. So really try and not make it more complex than it needs to be.
Yeah, Alex, I always do check the coverage report incrementally in between fuzz runs. And like you said, I try and write the minimum code, and then I run the fuzzer, check the coverage, and then I try and write a bit more, wrap another handler, run the fuzzer, check the coverage, and I'm looking to see that my coverage is advancing. And there has been times where I expected the coverage to advance and it didn't. And then of course, I had to ask the question, oh, why didn't the coverage advance here when I expected that it would? And there has been times when I found interesting bugs just from that, from asking then answering that question. So yeah, I think that coverage is very, very important, and continually checking that your coverage is advancing and you're getting to where you want to go.
Yeah.
Yeah,
So yeah.
One
go ahead,
technique might
just
also be useful a tactics. As a tactic is to just introduce bug into your program and see if the fuzzer can cut it. Because this is going to do an indication for yourself if your invariant is actually doing anything.
Yeah, this is objectively a good advice. And the most extreme version of this will be that if you have the luxury, you will write your invariant suite, and then you will go into audit, and then any bug that is found via audit, you will then want the fuzzer. Because most of the times, the bug that you miss, some of the bugs are massively complex integration gotchas, and it is what it is. But most of the times, the bugs that you do miss on the fuzzer is because you maybe you reached full coverage, but you still didn't try some very meaningful state transitions. And so this idea of having kind of a blue team versus red team, where you're trying to build a suite and trying to build the internal knowledge, and then the auditor is kind of finding some stuff that you forgot, and from that you then improve your own internal process and your own internal tests. That makes it so that over time you just write safer code by default. So that's the extreme version. And yeah, I think that's what we're seeing from the most advanced teams is the first time they do all of the work at the end, right? They do, I don't know, 3 audits, 5 audits, 7 audits, but it's all at the end. Whereas once they go the second round, they understand that if they just spread these engagements more over time, and then they also do more work internally, for example, through fuzz testing, they fundamentally just get better results because they introduce less bugs. So from my perspective, we can go into the next talk. I'm gonna try and keep it brief. I'm gonna share my screen very briefly. The next talk is called Echidna Made Me Do It, and it starts literally with a catch-all clause. We donated 15K to Echidna Medusa. I hope we continue to do this. My goal will be to check the platform, and based on how much usage we get, we will give a percentage to all the open source tools we use. And so there is really no hate in this stuff that I'm about to say. I believe I'm possibly a power user of the tech, or maybe I'm just a dork, but fundamentally I'm gonna go over some of the stuff that we went through this year, which happened through 14 different suites for 6 customers. Our customers tend to be repeated customers, and so we end up writing some big suites, but also just ordinary small suites just to make sure they ship. And then we've also been running cloud fuzzing for Badger, Corn, and Centrifuge. You can see our usage is 8,000 hours of fuzzing. That's an estimate over 7,000 jobs. And we basically broke about 150 different properties. You could say some of these are bugs, not all, but we found about that type of stuff. So the way we did it was by following the Chimera framework, meaning we fundamentally build Foundry tests. We run Echidna and Medusa to break them, and then we debug them in Foundry. We've linked this multiple times, but you can check Chimera and our Create Chimera app. And our workflow tends to really be kind of streamlined, where we have a scaffolding phase where you just set up stuff, a coverage phase where you want to get to a meaningful coverage. Obviously, you want to reason about what you're doing, but at the end of the day, you want to see the line get green, not red. And then you have the property specification phase, which will be one where you either have to adapt your test in order to test the properties, or you would have a more of a mental exercise where you go through the code and figure out what can go wrong and the type of properties that you will want to test. And so the key is really that we use Echidna and Medusa every day. I go to bed, Echidna is running in the cloud, I wake up, I get the feedback, and I kind of iterate. And that's just how it works. It works really well for us. But that also means that we end up finding some of the oddities of the tool simply because we rely on it for fairly mission critical aspects. And in terms of results, we got most of these are eventually gonna have a repro, but as for now, I can only say we used Echidna to find a $300 million voting attack. We were able to mint that amount thanks to the optimization mode. I recently found an incorrect pricing formula that caused a 1000x loss to arbitrage. We found multiple issues with many ERC-466 vaults. At the beginning of the year, I found a way to manipulate an oracle for a simple donation. And then we also found more of the bread and butter, denial of service on vaults and encoding, decoding bugs. So we definitely found a bunch of stuff. And we also had quite a lot of things go wrong. I think the first thing that I'm really going to talk about is linking libraries, which tends to be such a simple idea. And it also is as a simple solution. And yet many customers and even my own team, they just get stuck on something like that. So I feel like linking libraries is something that can be solved through the toolings or through better education, but it's fundamentally a barrier to entry that should be removed. We encountered a couple of bugs with HEVM very recently, and obviously these are patched, but at the same time, I'm going to talk about what happened. We also are currently, living with Echidna not fully shrinking sequences, which is something that we have a sidestep for. I'm going to show what it is, but Hopefully this gets fixed, because to me, optimization mode is an incredibly useful mode. And then we have found some weird stuff when forking the chip, which I'll show how we solved it. And lastly, we also ran into a performance issue when upgrading blindly to Medusa. So you do have to be a bit mindful of this stuff, but at the same time, again, this comes from a place of love. And also, I'm going to talk about a couple of the mistakes I made. So the first thing is, linking libraries is basically the dark souls of invariant testing. Anytime you have a library that says external, most people are unable to test it. And this is the answer. This is how you solve it. You have to go in the Echidna config and Medusa's identical config, and you have to deploy each contract or each library to an address, most likely above a precompile. That's why F01 is just the address high enough above a precompile. And then you will just pass it via the critic args, via the compile libraries flag. And this solves the issue for every customer every time. It always solves it in the same way, which is why I'm a bit perplexed as to why it's not automatically handled via some sort of a default address that is automatically decided by Echidna and Medusa. I feel like that's what it should be. But at the same time, every time my team runs into this, I'm like, just send me the code, I'll fix it. It typically takes 10 minutes to fix. However, for most people, this tends to be a big hurdle that most of the times forces them to change the library from external to internal. That's just my experience. People don't really do that. The other thing that we are getting is start prank. Very recently, HEVM introduced this Foundry-inspired cheat code. And I love start prank because currently the best practice consists of deploying these contracts that effectively are proxies. They basically just, you have Echidna tell it what to call, and then it will call it. And it's just literally a way for you to have a different address performing the call. And so all of the target functions end up looking like this, where you have to use this low-level ABI encoding, which I always thought it's a very strong barrier to entry because it just introduces needless complexity. And so the promise of start prank will be that you will simply enable an actor, start pranking it, disable an actor, and stop pranking. However, once we actually did it in prod, we ran into a bug where at all levels of the stack or at all levels of a call, HEVM was always assuming that the caller was the pranked address, meaning that every transfer was always having the message.sender set to the pranking address instead of whatever address was being called. And so that basically made it so that all of our tests will break for literally no reason, or the coverage didn't work. And so we had to basically benchmark it and figure out what went wrong. And it turned out there was this bug. You can see it on issue 608, which is solved. It's now done. However, that forced us to go back to our good old inline pranking, which is considered a smell by Trail of Bits, but to be it just is what it is, I guess. But that's an example of trying the newest release and unfortunately that backfiring. There's another issue that is still unsolved as far as I know, which again, the promise of the fuzzer is that you could call any address with any data. So if you ever are so uncautious as to literally put an arbitrary call to an arbitrary value, anytime Echidna tries to call the 0A, which is a precompile that is not implemented by HEVM, it will actually self stop one of its workers. And once you run out of workers, Echidna just stops running. It basically just stops because it's like, my job is done. And so that's just the quirkiness of it. The sidestep is really easy. You just require that whatever arbitrary address you call is above a certain address. However, it's one of these gotchas that hopefully will get solved and hopefully also doesn't drag you down. Another thing that is unsolved in Echidna is optimization mode, which to me is basically one of the greatest things in Echidna, because you can simply replay your corpus and just try optimization mode to see if you can generate massive values instead of relying on this common pattern where you just set some arbitrary threshold, which from my experience doesn't really work most of the time, because once you actually put a specific function in optimization mode, Echidna actually tries to break exclusively this, meaning that it tends to find better answers than if you just put a random threshold. However, this is what our $300 million exploit looked like. It's basically Echidna saying, good luck, maybe you'll find the root cause. And thankfully, Gustavo from TrelloBits helped us go through the process to actually get Echidna to run a shrinking sequence, which effectively requires you to take the optimization reproducers, paste them into the coverage, and then rename your tests to be property tests. And then you basically actually get shrunken logs. However, hopefully none of you has to go through this because it will be fixed soon. Because this optimization mode is so good, it's worth, currently it's literally worth going through this for me. Another bug that recently happened to our colleagues, but we dealt with at the beginning of the year, is that if you ever forget to send the block number to Echidna, and then you also forget to roll, you basically enter this no man's land where weird stuff can happen. Sometimes Echidna uses a default block, sometimes you get a segmentation fault. To be quite honest, I'm not exactly sure what the issue is. However, our team internally has agreed that anytime you do fork testing with Echidna, you have to pass the block number and then make sure that the vm.roll and vm.warp are the same value at all times, because anytime one of the values is different, you basically enter an undefined behavior. So that's how we currently solved it, although I have no idea what the root cause is. The last issue we ran into was Medusa 0.15. It just felt slower. And so we basically put both on staging and we ran some benchmarks. And it turned out there was a change that made it a bit slower. And so this is just the downside of trying bleeding edge attack and bleeding edge releases. This is why internally we would always run the tool at least a week before updating it, because you never know if something gets broken. But this was fixed in one day, so it turned out to not be an issue. But it's a good reminder that you want to benchmark stuff. You don't want to just blindly, yoink it, I guess. This is one of our bugs instead. Our Create Chimera app didn't have a default sender, the default deployer in the contract address. Because of missing that flag from Echidna, all of our tests that were broken in Echidna wouldn't be reproducible in Foundry. So if you use the newest version of Create Chimera app, that's fixed. And now all of your repros that use hard-coded addresses from Echidna are fully compatible with Foundry. That was a mistake we made. And another mistake we made is we still are unable to parse some of these bytes and structs. It's just a bit complex for our scraper. We'll eventually figure it out, but it just shows how, on one end, we were able to go really far without figuring this out. And then on the other end, it shows you how, you just have to use stuff a lot before you end up fixing it. So the question at the end, was it worth it? From my perspective, the learning curve of these tools is still very, very, very high. It can be very frustrating, especially the external libraries, or even just the idea of having target functions, etc. I hope with Chimera and with Medusa, these things are getting a lot easier. And that's what I believe is that simply by us doing this so much more often, it's gonna get so much easier. And at least for me, having done it so often, it does become worth it. Although I think for most people, the first 6 months tend to be brutal in comparison to just doing manual review, for example. So in the future, I hope we basically eliminate the need to scaffold. Currently, our internal goal is to get to 3 days to full coverage, meaning that we scaffold for 3 days and we have 100% of all state transitions. We'll see whether we're able to do that, but hopefully one day we get to such a sophistication of the tools that we don't even need to scaffold anything. We just write the properties, write some ghost variables, and then all of the, maybe we provide the setup, the deployment, and then everything else is given by the tool. So that's my hope for the future. And hopefully if you watch the Medusa presentation as well, you're going to join us in making that a reality. So we'll answer one question, and then we're gonna get right into with Benjamin's main event. So we have a question by Jason, probably a dumb question, but I'm currently a crypto wallet infra hacker as my job, API client-side wallets, but I'm dabbling in Web3 side of hacking last few weeks. I find it fascinating and fun, but I still need to pay the bills. Does it seem like the Web3 security field is growing and still needs more people doing audits and fuzzing and invariant testing? What would you say, Josselin or Benjamin? Are you guys still hiring and growing the team, or do you think do you see a change in the market?
So we're hiring actually. So there's still a need in the market. I do believe at the same time the entry-level security researcher kind of space has grown to a point where it's really, really competitive to get into it nowadays. But there is still at the same time a lot of opportunity. In particular, like if you want to learn with bug contest or on the side, there are a lot of opportunity nowadays. So I think you can still make a good career there, but it is competitive, so you have to be aware of that.
Yeah, I will mirror that statement. I think this is the year in which, or 2025 will be the year in which competitive contests are going to be more of a marketing tool than necessarily a security tool. That's the pivot that we've seen in the past 6 months. But from my perspective, in terms of learning and in terms of impact, this space is still growing a lot. And also the problems that are unsolved are still the same. People getting phished every day, people sending money to the token or the other zero every day. And so I think the space is literally has the same problems. So if you're open to solving those, I'm sure you can make a great living and find an awesome job as well. So without further ado, I'm gonna share my screen for 2 seconds. We have the main event of our talk. Let me send it on Twitter as well. This is we just had to do this as the main event, right? Uniswap v4, one of the most ambitious code base, highly optimized, pushing the EVM, needing literally an upgrade just to be able to ship it. And we have is the senior security engineer at Trail of Bits, specializing in stateful fuzzing and node software, author of Critic Properties and the Ethereum node chaos fuzzer called AttackNet. This is Uniswap v4 taking invariant testing where minor review cannot go. Let me hear your emojis for Benjamin.
Right. Can you see me and hear my screen, or see me, hear me and see my screen?
Yeah, looking great.
Perfect. All right, let's get started. A little bit about me. I just kind of got an introduction, so I don't need to go over most of this. I'm a senior security engineer at Trail of Bits. We help developers build safer software. We also maintain some popular tools, Slither, Echidna, Medusa. If you guys want to follow us on Twitter, there's a QR code. You can also get this from the slides that will be linked in the chat below. But let's just dive right into things. So this is kind of the overview of what we're going to talk about. It's split into 2 sections. First, we're going to talk about why you would bother with fuzzing at all. I know you guys have heard a lot about this in the past 4 hours, but we're going to focus on why you would bother fuzzing during like a security engagement, during an audit. And then after that, we're going to talk about what the actual right way to fuzz Uniswap v4 would be, and how you would actually implement those invariants, because there's a lot of different ways to implement them. And that's part 1. After part 1, we're going to kind of turn up the technical heat, and we're going to talk about how the sausage was actually made, because this was a very challenging set of testing suite to put together, and it was really interesting. And I think you guys are really going to get some good tips out of hearing about the struggles that we had. So first, why bother with fuzzing at all? So you've got a contract, you've got a protocol, you've got something. It can have all kinds of different states that it could be in on chain. And some of these states are going to be bugs. They're going to be something that you want to never be able to happen, and you want to be able to detect those bugs. The first thing that you would usually do is to write unit tests. And unit tests are great. They help you explore some of this state and verify it. But the problem with unit tests is they only test one specific state or one range of states for each test that you're going to be writing. So they're very limited in how much they can actually explore the space. So what do? You get an audit. And an audit can also verify a bunch of states, including states that you can't reach with unit tests. A good example of this might be something that like an emergent behavior that the developers like aren't thinking about when they're writing their unit tests. You go to the auditor and the auditor is like, well, what about this case? So there's some states in here that you can verify with the audit that you can't verify with the unit tests. But like overall, during an audit, like because it's a time boxed engagement, most of the time you're verifying a fewer number of absolute states than a good unit test suite could be verifying. So it's really, really important that when you go into an audit, you're not trusting the audit to find bugs. You need to start with your unit tests because that's the best place to, get most of your coverage initially. But then let's talk about fuzzing. So fuzzing is unique in that the state of your system, you have no idea what state it's going to be in when you run your test. When you're running a unit test, what you're going to be doing is you're like deploying your protocol, you're configuring it, you're setting up tokens, and then you do some things to run your unit test. So you always know the state that the system's going to be in. But when you're running this fuzz testing, you have no idea what state the system's going to be in. So you get a much, much wider coverage than you would even with a manual review. And then people always ask me, well, what about formal verification? Can't formal verification actually verify this whole big red bubble? Because, it can test all possible states. And the truth is a little bit more nuanced because formal verification, while it can theoretically test all possible states, you're limited by how effective the formal verifier actually is. Because like if you were to write something that would verify all of the states, it would take longer than like the heat death of the universe to prove the proof. So you're limited by what is actually provable. And for almost all cases, that's going to be a subset of the states that are verifiable with fuzz testing. Now, this diagram, if you're big on formal verification, you're probably like shaking your head about this diagram. Don't worry, we're going to revisit it in like 20 minutes, and we'll clear up why this isn't exactly 100% honest. But with that in mind, let's talk about our engagement with Uniswap. So we had this 3 calendar week audit that we were going to do with them for this protocol that has really, really high arithmetic complexity. It's very compact. It's very like painfully complex. There's a bunch of potential issues for rounding, path independence errors. It's just a complete mess. And so we had to figure out how would you allocate resources to obtain the highest coverage possible. Because like we only have 3 weeks. And this protocol has already been reviewed by like 4 other audit firms. So it's not going to be easy to find bugs. So what we decided to do is we would allocate 1 engineer to build a fuzzing harness to try to find the bugs that auditors normally have trouble finding. And the good thing about this means that the auditors can now focus on finding the bugs that they're really good at finding. They can now ignore the bugs that they're not good at finding, and the fuzzing harness can kind of like pick up the slack and work on finding those bugs that the auditors just aren't very effective at finding. So next, let's talk about how we chose to fuzz Uniswap v4. We had a couple of goals here. The first and most important goal is we don't want to duplicate any of the previous auditors' work unless we had a really good reason to do so. Certora had audited right before us, and they did a whole bunch of formal verification stuff. It would have been pointless for us to duplicate that work or to like, make a superset of that work because they had already formally verified it. There's no point in doing it. We also wanted to focus on properties that are hard to manually verify because we're trying to use this to aid the auditors. We're trying to take stuff off of their plate and use the fuzzing harness to be able to find the stuff that they don't normally find. And last, we don't want to bite off more than we can chew. Again, this was only a 3 calendar week engagement for a really complicated protocol. So it was really, really important that we don't like try to exhaustively fuzz absolutely everything about it. So we made this decision. We were going to, for the time being, ignore hooks and focus on end-to-end modeling of assets versus liabilities. And this is basically the core thesis of what our fuzzing harness does. And so like, let's talk about assets versus liabilities. It all boils down to basically one property. The protocol's assets always have to be larger than or equal to its liabilities. And so what does that actually mean? So I'm going to put up a little thing of assets and liabilities for a theoretical AMM. For the assets, you would have like the tokens that are in the contract that can be spent by the contract. You also have the flash loan receivables. So when you take a flash loan from a protocol, the tokens in the contract go down, but it's guaranteed that you're going to return the flash loan by the time your transaction ends. So that also counts as an asset for the protocol. And then on the liability side, you have everything that the protocol owes to people. So if it's an AMM, it's going to be owing some amount of liquidity to LPers. It's going to owe some amount of fees to LPers. If there's some kind of like staking mechanism, it's going to owe some amount of tokens to users. And the goal here is to model and keep track of all of these assets and liabilities and verify that the assets are always greater. So what does this look like? In Uniswap v3, so you get a pool contract deployed for every single pair and every single like fee tier in the pair. So we have two pools here. We have a USDC ETH pool and a USDC rug coin pool. And each of these pools is going to have two balance sheets. The first one has the assets and liabilities for USDC and the assets and liabilities for ETH, and the other one has the same thing. And what's important about this is if we were going to go in and try and write properties for it, we would need at least 4 balance sheets, 2 for each one, and we'd have to keep track and make sure the assets for each one don't exceed the liabilities. And what's really nice about this design is that if something bad was to happen to Rugcoin, but you know, it's a Rugcoin, something terrible was to happen, even though that this pool uses USDC, that's not going to impact any of the other pools that happen to use USDC because it's a completely separate contract. Like one pool can't borrow tokens from another pool. And this changes in Uniswap v4 because Uniswap v4 uses a singleton contract. So all of the assets from all of these pairs are commingled. So now instead of having to have like 4 balance sheets, you would have to have 3. This is much riskier and actually much more complicated to track because Uniswap doesn't actually give you a way to ask it how many USDC assets are associated with the USDC ETH pool, how many ETH assets are associated with the ETH RUG-C pool. So tracking this gets really, really tricky. And we have to start thinking about like, how do we actually implement this? In the interest of time, I'm just going to go to the approach that we actually did. There's 2 ways to do it. If we have time at the end, we can talk about the first way. But the way that we ended up going with is to explicitly track the assets and liabilities. And so, as I mentioned a minute ago, the V4 design doesn't allow you to ask the singleton contract how many tokens are in a pool. So that causes a lot of problems for us who are trying to track how many tokens are associated with each pool so we can model the assets and the liabilities. There's also some other problems from gas optimizations. So like when you do a swap, like a basic swap, a certain amount of your swap is going to go towards fees for the LPer. And there's no way to figure out on chain how much of your swap went towards fees without basically completely simulating Uniswap within your contract. It's a huge nightmare. Another thing with Uniswap v4 that's very tricky is it has this new settlement system. So everything in Uniswap v4, you can't just interact with it willy-nilly. You have to call unlock, and then it calls a callback. And then from the callback, you do all the interacting with Uniswap. And what that lets you do is it lets you do like flash loans without having like to explicitly call anything. You just say, hey, give me some funds. And as long as everything is balanced out at the end of your transaction, it won't revert. And so now that settlement system on its own needs its own assets and liabilities to keep track of what has the user borrowed and what does the protocol owe to the user. And so we ended up having to model this using something called shadow accounting. And this is a technique that you could reuse for any other protocol to model its assets and liabilities. But the idea here is we have this contract that sits between our fuzzing harness and the Uniswap contract. And instead of directly calling into the Uniswap contract for anything, it's all going to go through this shadow accounting contract. And this contract keeps track of all of these variables, like for each pool, how many swap fees are owed. For each pool, how much liquidity is owed to LPers and how many protocol fees are owed. And so when you call into this from the fuzzing harness, it tries to figure out how many tokens are going to be added to the balance sheet, how many tokens are going to be removed from the balance sheet, how is this going to change the assets and liabilities, and then it goes and forwards the call to the Uniswap v4 contract. And this lets us do this thing where we can basically just assert swap fees plus liquidity plus protocol fees is always less than or equal to the assets, and make sure that the liabilities are always less than the assets. And this is like roughly the direction that we were going in. And like basically all of our fuzz testing was about how to do this as exhaustively as possible. And that's where we're going to kind of go into the part 2 here. And this is the interesting stuff. So that harness that we decided to build, it turns out there's some things about Uniswap's design that actually broke everything that we knew about our fuzzers. And so we're going to talk about fuzzing. We're going to talk about how fuzzers work. We're going to talk about how Uniswap broke it. So buckle up. If you're not a fuzzing practitioner, by the way, this part of the talk might get a little bit like challenging. Don't feel bad if it gets challenging. Just come back later when you've tried fuzzing something, and everything will be all right. So for this part of the talk, we're going to talk about a couple of different things. First, we're going to talk about this callback mechanism that v4 implements and how it breaks absolutely everything. From there, we're going to talk about how fuzzers work. There's a bunch of hidden conjectures inside of fuzzers that dictate how they actually discover new states. And there's some critical stuff about that that gets broken. And then we're going to talk about some of the band-aids we applied. The first one being called state space enrichment, and the second one called path discovery. And these band-aids are things that you could apply to like, any fuzz testing suite. So even if you don't plan on fuzzing Uniswap, you can still reuse these for your own protocol that you're working on. And then last but not least, how do we know that any of this actually works? Because this is a fuzzer. Everything is fuzzy. It's not always clear what is actually getting covered or not. So it's very important to figure out if it actually works. So let's talk about v4's callback mechanism. So in v4, everything is happening through a callback. And if that didn't make sense earlier, I've got this nice little picture here to explain it now. So everything starts with the user. So the user can't directly interact with the singleton because the singleton always needs to do a callback. So when you're an EOA or you're a fuzzer, you have to interact with Uniswap via some kind of router contract. And this router contract is what's actually going to be doing all the interactions with Uniswap. So let's say you're going to do a swap. So you call into the router contract. You're saying, I want to do a swap. The router contract is going to call the Uniswap v4 singleton and call unlock. Then the v4 singleton is going to do this callback. And this like dark blue bar here is where all of the interaction with Uniswap actually happens. So that's where you can sync, swap, mint, flash loan, all of that good stuff. And then once you're done with that, you return from your callback. Uniswap right here is going to check to make sure that you've paid all your balances. You don't owe anything to the protocol. The protocol doesn't owe anything to you. And if it's successful, it's not going to revert, and it's going to return from this lock, and the router is going to return from the swap, and everything goes okay. But this provides some very big challenges for fuzzing, because normally when we're doing fuzzing, we don't want to just call this high level swap. We want to be able to call all these like little functions that Uniswap implements: the sync, the swap, the mint, the modify liquidity. And so we ran into this problem where there isn't actually a way for the fuzzer to directly access these, because they all have to happen in this callback. And there's no way to like pause the fuzzing execution to like do these things in the callback. So we started building a harness that would work around this. And the way that this harness works is we have a contract called the action fuzz entry point. And what this does is it keeps two lists, a list of actions that are going to be executed during a callback and a list of parameters that are going to be executed during a callback. And so when Echidna wants to call something in Uniswap, instead of calling directly into Uniswap, it calls the harness and it says, I want to add a initialize action. I want to add a swap action. I want to add a mint action along with the parameters. And it adds these parameters to the list and then returns back to the fuzzer. And then eventually the fuzzer is going to find this new function called run actions. And this does exactly what it sounds like. It's going to take all these actions that we pushed into this list and execute them all at once in the same callback. So we run execute actions. This is where the interaction with Uniswap actually happens. It calls unlock. We get the unlock callback. This spot right here is going to go through and it's going to run all the actions in sequence. If everything is successful and like all the balances are canceled out, it's not going to revert. It's going to return from the unlock, return from execute actions, and then return from run actions. And in theory, this like looks like a good design because it allows us to like get into these like low level functions that Uniswap implements. And now we don't have to like abstract a bunch of stuff away. But unfortunately, this is wrong. And this is like really, really fundamentally wrong. And we didn't realize it until like a couple days after implementing it. And it's like, why won't my coverage go up? But it turns out that this design of the harness breaks everything about what the fuzzers are expecting for like how coverage increases and a whole bunch of other stuff. So next, we're going to talk about the hidden conjectures in fuzzers. And this is a little bit about how fuzzers actually work. So here's this picture again from before. I had mentioned that, there's this amount of states that are verifiable with fuzz testing. You have this amount of states that you could theoretically do with formal verification. And the truth is this graph should be a little bit more like this. And the reason it should be a little bit more like this with this, this like kind of like noise pattern here is because when we're running fuzz testing, it's not concretely executing every single state within this circle. It would take a very long time to do that. Instead, what the fuzzer is trying to do is the fuzzer is trying to figure out what states do I want to reach? What states are going to be really interesting? And it tries to figure out how to provide inputs to get to that state. And the idea here is that even though it's not covering every single little pixel inside of this circle, the pixels that it does cover are the ones that are the most interesting. And it's really important when you're trying to figure out like which pixels do I want to cover. Like how do you actually get there? Because like you could like just randomly generate like parameters, randomly generate functions, like do this random walk, but then you'll get pixels that are all over the place. Like you have no guarantees that you're getting the interesting states. You have no guarantees of like coverage or branch coverage. It's just a really rough time. And with formal verification, like this is the one thing that formal verification really has for it is they don't have to worry about this at all. When you formally verify this little bubble right here, it's correct for all of those possible states. But the trade-off with that is that means you can't really model larger, more interesting properties like assets versus liabilities because it's just too complicated to prove. So the question is, how does the fuzzer figure out which points are going to be interesting? How does it figure out how to get to one of those points? And that's where hidden conjectures come in. So a hidden conjecture in this context, I made up this phrase, hidden conjecture, because it seems like there's no other thing that people call it. But it's an idea that the fuzzer uses to try and predict what inputs are going to increase coverage. So here's an example. So we have this sequence right here where we're going to call F, we're going to call G, and we're going to call H. And the idea here is that if H gives us new coverage, then it's likely that adding another transaction after H will further increase coverage. Now, this is something that we're guessing is going to be true a large percentage of the time. There's no way to prove that this is always correct. And if you're like a PhD student or like a master's student looking for a thesis, if you could find a way to prove that this is correct for like a certain subset of programs, please do that because it'd be really, really helpful. But for most people, it's not intuitive why this would actually be something that increases the coverage. So like, let's give like a better example here. So here's an example sequence that might make a little bit more sense. So we have this sequence where you initialize a pair, you transfer tokens, and then you add liquidity. And all three of these transactions succeed. And when you call add liquidity, it increases your coverage. Now, from an intuitive point of view, like let's say this is an AMM or something. Now you know that you could probably do something like calling swap and be able to succeed and further increase your coverage even further. And so this is a situation where this conjecture is true, and adding another function is likely to increase coverage, even though we don't know what it's going to be yet. And so fuzzers are full of these types of conjectures where there's like a guess, like if this and this and this, then doing this will increase the coverage. And the important thing to take away is that these conjectures aren't always true. You can construct a program where this conjecture will always be false. And this also tends to have like some big problems when it comes to benchmarking fuzzers. It's very easy to accidentally write a fuzzing benchmark where all of the like it works really, really well for one specific conjecture, and the rest of the conjectures just don't apply for it. So if you're like thinking of writing like a fuzzing benchmark or something like that, please like try to do some research here about like what these conjectures are in different types of fuzzers and try to provide some diversity. It's like in an ideal world, we would want to be able to have just real world contracts being tested, but there's really not enough bugs out there to like do a good benchmark. But this is hidden conjectures. The reason why I call them hidden, by the way, is because just nobody talks about them. There's nothing actually hidden about them. So this hidden conjecture that we just talked about is broken by our harness. How is it actually broken? So we have this is our harness that we just talked about. And what it's going to be doing is it's going to be calling add initialize, add swap, add all of these things. Each time it calls these calls are always going to be successful because they're just adding an action to the list. They're just adding parameters to the list. They're always going to be creating coverage. And even if you create like a add swap that's completely invalid, it's still going to be adding coverage, and that's not good. And the thing that makes this really challenging is that the only point at which we're actually interacting with the Uniswap v4 contract is in run actions. So now the thing is, the fuzzer is like, well, run actions is the thing that's increasing coverage, and it has a harder time to figure out that, this sequence is successful because of one of these add swaps or the add initialize, not because this run actions is being called here. So let's talk about how the fuzzer would theoretically figure out how to do a swap. Well, it'd have to call add initialize, it'd have to call a bunch of stuff to set up the pool, it'd have to call add swap, it'd have to call add sync, it'd have to call add settle. There's actually a lot of calls that it takes to Uniswap to actually be able to set up a pair and be able to do a swap and like to settle everything out. And at the end, you still have to call run actions. If you got everything right here and you didn't call run actions, it's not going to work. And the other thing is, after you do call run actions, if you were to call add sync or add swap afterwards, it's not going to increase your coverage. It's not going to be successful. Because remember that what that conjecture was before is that if we have coverage in this last function here, adding another one after is going to increase coverage. But in this, after you run the actions, all of a sudden, all of this gets reset. If you want to do another swap after you run actions, you're going to have to add swap. You're going to have to transfer tokens to the harness. You're going to have to call sync. You're going to have to call settle. And then you're going to have to call run actions again. So in essence, this conjecture is completely broken. And in most cases, like 99.999% of cases, it's not going to work anymore. So I like visualizations. So this is like an arbitrary like visualization of like how this works in practice. So you've got these random input parameters that the fuzzer is thinking of, literally just random numbers that it's using to like figure out what sequence am I going to use, what parameters am I going to use for that sequence. And depending on which random numbers it uses, there's a chance that it's going to increase the coverage. So like, you got this little hill up here where if it selects any of the random numbers in here, we're going to get a really big increase in coverage. If it selects one of these dark blue sections, it's not going to get a big increase in coverage. And this is what it looks like when the conjecture works. But if the conjecture doesn't work, then when you select those random numbers, it's not going to be creating a sequence that's likely to increase the coverage. And so all of a sudden it becomes much, much harder to be able to increase the coverage for a given set of random parameters. Let's see. And the thing is, like, where this is causing problems is that now the fuzzer is trying to spend time trying to like work a conjecture that just doesn't work. And so sometimes we can get results that are even worse than like a random search or like a random walk. And that's like a really bad situation to be in. So let's start talking about the Band-Aids. We have a couple of different Band-Aids that we use to like try to fix this on the spot. The first is something called state space enrichment. So there's a couple of different approaches we could have taken to fix this. The first and like most obvious approach that would come to most people is to make changes to our fuzzers to change the relevant conjectures. There are ways to like move the conjecture around or adjust it to make it more true for this specific Uniswap case. But the problem is, again, we only had 3 calendar weeks to do this. So making a big change to the fuzzer during the engagement was just not a good idea. So our backup here was to enrich the state space. What do I mean by state space enrichment? The idea here is that we want to make it way easier for the fuzzer to detect high quality sequences and to stick them into the corpus. And we do this by explicitly telling the fuzzer what kinds of things do we think are going to be interesting. And so we've got some code here. This is for run actions, that one function that happens at the end of these sequences that actually executes everything. And so we're doing all that interactions with Uniswap in this like ellipses right here. And right after it, we're going to be adding some additional code. And this additional code loops over all the actions that we just ran successfully and checks to see, was there a donation? If there was, set this Boolean flag to true. Was there a successful swap? If there was, set this Boolean flag to true. And then at the end of this, we have this conditional statement here where we check if there was a donation and a swap in the same sequence of actions. And if there is, emit this log string. And what this does is this basically tells the fuzzer, hey, there's a specific type of state that I think is really interesting. And by adding this conditional right here, we've created code that now the fuzzer can cover where originally there wasn't any code. So if there is a transaction, or if there's a action sequence that contains a donation and a swap, now this code is going to be covered, and now we're also going to get it added to the corpus. So now the fuzzer can take this transaction that we told it is going to be interesting and start doing mutations on it. So and also this other thing I forgot to mention. You could also use this to figure out if the fuzzer is working in the first place, like by adding these like canary logs like this. So whenever you run a fuzzing campaign, you always want to check the coverage afterwards to make sure you had good coverage. By adding something like this into your test harness, now you can go and look to see if this line of code was actually hit as well. And if it was hit, then that is a condition that your fuzzer was looking at. And if this was never hit, then there might be something wrong with how you set up your fuzzing harness, or something wrong with how the fuzzer is like finding sequences that's preventing this from being hit. And it can be a good way to like start a conversation about like, is my fuzzing harness like actually working? Okay, so now let's talk about the other Band-Aid, path discovery. So what is path discovery? This is another thing I want to illustrate with an example. Let's look at Uniswap v3 really quick. So in Uniswap v3, let's say we're fuzzing Uniswap v3. We don't have to have anything weird in our harness. So it's just like a normal fuzzing harness. And we're starting out with like a freshly deployed Uniswap v3 instance. And the fuzzer is trying to set up like its first initial sequences. So it sets up 3 sequences, one that calls swap, one that calls modify liquidity, and one that calls new v3 pair. So when we call swap, this is going to revert, and there's not going to be any new coverage. Why is it going to revert? It's because we just deployed Uniswap v3. We don't have any pairs. We don't have any money in it. We don't have anything. Same thing happens when we call modify liquidity. We don't have any pairs deployed. There's no money in it. It's just going to revert. It's not going to cause any changes. But when we call new v3 pair, it's going to succeed. And when it does succeed, it's going to create a new coverage. So like you have all this code that is now being covered that was not previously being covered. And that means this sequence is going to get added to the corpus. And so at this point, we have our corpus, and it just has this one transaction in it, or this one sequence in it that contains this new v3 pair call. And it's not hard to see how over time, Now that we know how the corpus works, the next time it's going to start with new v3 pair, and it's going to be adding calls after it. And it's going to add something like modify liquidity. And oh, would you look at that? Now that increases coverage. And then now that we have this one that has new v3 pair and modify liquidity, it starts adding more transactions, and it sees, oh, I can actually call swap now. And so this is how a fuzzer goes from like not knowing anything about your code to being able to know about how to actually do a swap. And this is a really important property, because if you go from like an empty corpus, if there was like nothing here, it'd be very hard for the fuzzer to go from nothing into knowing I need to call new v3 pair, modify liquidity, and swap. It's very probabilistically unlikely that the fuzzer is going to be able to do that without first discovering, first I have to call new v3 pair, then I have to call these two, and then I can call all three. So this is really important. And of course, v4 breaks it. So here we have three sequences, same situation. This is a freshly deployed v4 singleton, and we're just calling these three sequences. When we call add swap, unlike before, this is actually going to succeed. And that's because add swap is not actually interacting with Uniswap v4. It's just adding this add swap function to the list of actions that we're going to be calling when we call run actions. So this is going to succeed. It's going to create new coverage, and it's going to add the sequence to the corpus. The same thing is going to happen when we call add take. This is going to succeed. It's not interacting with Uniswap v4, and it's going to add a sequence to the corpus. Same thing happens with add initialize pair. Same situation. It's going to succeed. It has new coverage. It's going to add the sequence to the corpus. So now what does our corpus look like? It has these three functions in it: add initialize pair, add swap, and add take. And because now our corpus has a bunch of these sequences in it that don't actually mean anything to us, it's going to be way harder for the fuzzer to figure out, well, I have to initialize the pair, then I have to add liquidity, then I have to transfer tokens, then I have to swap, then I have to like settle the balances with Uniswap, then I have to like call settle, then I have to call run actions. It's very, 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 very unlikely that based on this corpus, the fuzzer is going to figure out how to do a swap. It's going to be terrible. So how do we fix this? So the way that we fix this is using something called a shortcut function. And a shortcut function is similar to like the other Band-Aid. This is a way for us to define known good paths that will enable deeper coverage of the actions that are occurring. So I've got a couple of examples here. The first one is a shortcut, and these are functions that the fuzzer can call. This first one is called initialize pair and add liquidity. And so this is a shortcut for a bunch of different things. So when you call this, it adds add initialize, add modify position, add shortcut settle, which we'll talk about in a minute, and finally a run actions. And so whenever the fuzzer calls this, we know for sure it's going to be initializing a pair. That pair is going to have liquidity. All the actions are going to get run, and now you can start swapping on that pair. So this takes away a whole bunch of guesswork that the fuzzer originally had to do to figure out how to deploy a pair and actually add liquidity to it. The second shortcut function we have here is add shortcut settle. So what this one does is, the unique thing about Uniswap v4, again, is like the settlement system. When you do a swap, you don't necessarily have to provide those tokens yet. But you do have to provide the tokens and like settle your balances before you're done with your callback. So what add shortcut settle will do is that when it comes up in this sequence, the harness is going to figure out how many tokens does the actor owe to Uniswap v4, how many tokens does Uniswap v4 owe to the actor, and it's going to do all of the syncing, all of the transfers, all of the settlement calls to be able to settle all those outstanding debts between the harness and the protocol. And the idea here is whenever you call shortcut settle, if it's successful, when you call run actions, that will always succeed. And so that means the fuzzer can do all kinds of like really, really crazy, unusual stuff. Like, for example, if it's going to donate uint.max and then somehow take away that donation, trying to like trigger like an overflow or something. As long as there's actually enough tokens to settle that final balance, adding shortcut settle will allow that sequence of actions to succeed and actually try to increase our coverage and potentially find a bug. In the last example of a shortcut function here is add swap and run actions. You could have this happen right after calling like initialize pair and add liquidity. And all this does is it does a swap, it does a shortcut settle, and it does a run actions. And with these shortcut functions, all of a sudden it becomes a million times easier for the fuzzer to construct a working Uniswap v4 pair with liquidity that you can actually swap on and to actually execute the swap. And the nice thing about this is you could actually reuse all of this, all of these concepts at least in any kind of thing that you're fuzzing. Anything that has like really deep state that's hard to reach and hard for the fuzzer to like have an intuition about, you could create one of these shortcut functions for it and be able to make it a lot easier for the fuzzer to figure things out. So the last bit is, how do we know any of this actually works? Because again, like fuzzing is probabilistic. It's not hitting every state. How do we know that it's actually hitting the states that we care about? So we already actually talked about one of the ways to make sure that this works, and that's making sure that your coverage reports are as detailed as possible. So in the example from earlier, we had this conditional: if donate and swap happened and they were successful, emit this string. And so after you run a fuzzing campaign, you can look at your coverage report and see, was this line of code hit and run successfully? And if it was, at the very least, you hit the state where these two both ran in the same sequence of actions. And I highly recommend basically adding a bunch of these for states that you find interesting, because it'll make it a lot easier for the fuzzer to figure out what's going on. And it'll make it a lot easier for you to figure out if your test suite is actually working. The other thing you can do is inject canary flaws that the suite should be detecting. This is very similar to mutation testing, if you've ever heard of that. Mutation testing is where you inject mutations into the code, like changing a greater than to a less than, and then executing the unit test suite and making sure it doesn't pass anymore. Because if it does pass after changing a greater than to a less than, something's wrong with your unit test suite. And so we do a similar thing here, mostly in the form of adding 1 to random numbers. Like the number one flaw this should probably be detecting is rounding errors. So by adding 1 or subtracting 1 to certain spots in the code, we're essentially adding a canary to prove that our suite can detect when you add 1 to this, because now it breaks a bunch of properties. And that's basically it. This was a really, really fun engagement. We're really happy with how it turned out despite the challenges. The most important thing here is that, so the Cantina contest came right after our engagement, and the contest didn't find any bugs that were within the scope of our invariant test suite. So that's really good. If you want to go look at the test suite itself, there's a link to it here, and there's also going to be a link to it in the chat. It's on this add stateful properties branch inside of like the test directory. And if you want to contact me, there's my Twitter. And I think we're open for questions now.
Yeah, amazing talk, Benjamin. I actually have multiple questions myself as well, but before I drop those, let's hear from the Q&A. The first one is from Jason. I guess he says, the Uniswap router to the single total contract reminds me of shady proxy API middleware shenanigans. Do you have any comment on that?
What kind of shenanigans?
Shady proxy API middleware shenanigans.
Yes, it is similar. And the thing is, most people, let's go back to that picture because it's kind of a nice diagram. The thing is, most people are never going to be interacting with, this stuff down here. They don't really care about it. There's going to be like 3, maybe even 4 like normal flows that people follow for this. Those are going to be encapsulated in the Uniswap router, and nobody's ever going to know that any of this happens other than the MEV people. And like you could criticize that, but like it's also helpful because now the MEV people don't have to worry about, forcing their stuff to go through this actions router and making sure that like, they follow those patterns. So it's like most people aren't expected to go down to this level of complexity. It's just because we're doing this fuzzing that we have to care about it. If you were like integrating with Uniswap v4, I wouldn't care about this at all. I would only care about how you interact with your router.
Amazing. So I'm going to read one of my questions for you. It's off of the log string event. And my question for you is, would you say that adding a canary that breaks an assertion is even more interesting to the fuzzer? And are you saying that if there's no extra state change in this type of handlers, the fuzzer will simply not add the sequence to the corpus?
That is a really good question. So right now, when Medusa and Echidna do their fuzzing, they don't try to target certain branches for being broken. They don't do anything special to be like, I want to try to get into this branch. And that's kind of like that's something that certain fuzzers will try to do. Well, they'll be like, I want to specifically target this branch. But what is important is that just by adding this branch here, now we have a new potential item that could be added to the corpus. Um, I think that answered half your question. Was there another half that I forgot?
The other alpha is whether I guess I'm repurposing the other alpha, but the other alpha is if I put even more of those, I guess is that even better? So would you say you will put like I did donate, I did swap, I did donate more than 100, I did donate more than 10,000? Do you see extra utility in that?
There can be. So you get to keep in mind when you create new branches like this and new opportunities for items in the corpus, if that item is not valuable, if it ends up not being valuable, now your fuzzer is going to be spending a bunch of time mutating the sequence that isn't actually interesting. And so if I was to, add something here to detect if there's 100 donates in one series of actions, but I don't actually think there's going to be a bug in there. Now we have this really long sequence in the corpus to run 100 donates in a row. And it's going to mutate it and it's not going to find any bugs. So it's important that when you do add a canary like this, it's for a sequence that you think is going to be interesting to mutate. If you just do it for any sequence, it's not going to be valuable.
Okay, that makes a lot of sense. However, you said that an assertion versus just any sequence doesn't really have a bigger impact in the case of Echidna and Medusa. Meaning, at the end of the day, you're just telling it that this is one extra line to the core to the coverage, and so it's valuable just because it's one extra line. So let's go back to a very simple question. Would you say that a harness means a handler? Well, or is there a difference between a harness and a handler to you in your definition when building invariant testing suites?
That's a good question. I feel like they're the same thing. Um, in this case, where all of our properties were written and where all of our code was basically added was this one contract, action fuzz entry point. This contract had the shadowing counting stuff. This contract has all of our properties in it, has all of the magic included in it. So there's really only one contract. And then you have the actions router. This is something that Uniswap actually implements in their test suite. And then the Uniswap deployment itself. So we really only have 3 contracts and then the ERC20 tokens. So you only have like 3 or 4 contracts in the entire system. I don't have a good idea of what the difference is between a handler and what was the other one? A harness. Could you add some flavor to that?
So
Yeah, Bilal,
do-
if you want to add, go ahead. Feel free to go ahead, Josselin.
yeah, generally speaking, like in the fuzzing world, when we say harness, it's basically any piece of code that we are adding to target software to make it easier to fuzz. So we might have handler within the harness, but usually the harness is more of a, like you can have a lot of different things. It's basically any piece of code you are adding to help your fuzzer.
Okay.
I hope that
I
clarifies
guess
it.
from my broken English perception, I would say the harness is the entire thing, and a handler is one of the functions. So that's my understanding, but that's literally me using
You
the
are correct, and it was much better than my answer.
Yeah, so yeah, I guess that's the I guess a way of looking at it. So now we got an anonymous question. I don't understand your Venn diagram that contrasts fuzzing and formal verification about the if-def of the universe. Could you please explain? The whole point of symbolic encodings in FV is that you do not have to enumerate all possible states.
Yes. So imagine this is all possible states. So the fuzzer is not verifying each individual pixel. Instead, what it's doing is it's grouping together pixels. So like, let's say you have a conditional if x is larger than 5. So it's not going to check every single integer that is above 5, and it's not going to check every single integer that's below 5. It's going to just group that into two separate like execution environments. You have all cases where x is larger than 5 and all cases where x is lower than 5. And in essence, that covers all of the potential states for x being larger than 5 and x being lower than 5. It doesn't actually execute each individual one, but by doing that like separation, the grouping like that, it effectively does check all of them at the same time. Whereas with like fuzz testing, we're just checking individual states. So in that x is larger than 5, we'd be checking 1, we'd be checking 3, we'd be checking 20, we're trying to check very discrete states. And it's the fuzzer's job to figure out what inputs are actually going to generate those interesting states.
Yeah, from my end, if I can add one note, is that some FV techniques, I guess you would call it weakest precondition, would arguably not need the the time that will take us to the if def of the universe, because it will try to find some trick. But if you do, I guess the more bread and butter, almost naive like FV, where you basically each state transition is a node, then you do have path explosion, meaning that unless you have some sophistication, the definition that you see is technically valid. It's a valid interpretation. And then you would simply have to use tricks to go back to the states that you can actually verify before you get into path explosion. We have a couple of questions on canaries or shortcuts. Well, I'll read the one that is public and then I'll read you mine. The one from Jason is, are the shortcut function just essentially how a normal user will use the contract in a wide variety of ways that act as some sort of a cheat sheet to the fuzzer?
Yes, it is essentially like the flows that you know are going to create coverage. So going into Uniswap, we know there's a couple of flows. And you could actually find this inside of the harness if you go into the code for the action point thing. So we have initializing a pair, we have swapping, we have adding liquidity, then removing all of it later. Basically, all of like your user stories can become a shortcut function. But we don't want the shortcut functions to be the only way that the protocol gets tested. So something we ended up doing with Uniswap is we would first start testing without any shortcut functions and just see if the fuzzer could potentially generate one of these sequences. And the reason we didn't want any of the shortcut functions is we wanted to see if there's any really weird bugs in there if you're not calling the protocol in the way that it expects to be called. And once we were satisfied with the coverage for that, we enabled all the shortcut functions to see if there's anything even deeper than that. Because once you have the shortcut functions, they're also going to prevent certain sequences from being executed, because now you have these functions that gave us a whole bunch of coverage. Like, this is going to be a lot more valuable to run from the fuzzer's point of view than trying to like put together a sequence of like initialize, add position, run actions. As soon as you add these shortcut functions, there's a whole bunch of state that's very, very unlikely to ever be executed.
Wow, this is a awesome answer because it leads to my question, which is the more explicit question about this, which was, do shortcut help reach other sequences or are they treated separately? As in, would having a shortcut that adds, for example, free actions, would that lead the fuzzer to add them and then would also help it to execute the same atomic components of that shortcut? Like if I do, add initialize, add modify position, add shortcut in the shortcut, does it then lead the fuzzer into trying them more, or would it simply be treated as a separate function?
In this case, because we're only measuring the coverage when actions are being run, it's not going to cause, the only bias here is going to be, now we have a sequence that calls all of this in the corpus. And if you try to generate another sequence that calls these, it might not increase your coverage and it might not get added to the corpus. So it's like the thing is with these shortcut functions is they make it so that a lot of items that would normally go into the corpus are now not going to go into the corpus. But the trade-off for that is now that you have these items in the corpus that you know are going to be doing a lot of very complicated things. So it's almost like turning a conjecture off and then turning it on, because we're trying to get the fuzzer to explore one piece of that state space in the circle. And then once we're happy with that, we turn on the shortcut functions, and now it's going to move away from that and start testing a different part of the state space.
Wow, okay. This makes me think a bit. So I'm gonna ask you the follow-up to this is, but I guess that means because the way you call it shortcuts, we will call them clamped functions. Where you would have a instead of like because obviously you have a different context, which is that you preload the actions and then you execute them. But a more common example will be clamping a balance of tokens, clamping a target of addresses. And so arguably that will be a simpler version of a shortcut where fundamentally you reduce the inputs. And what we find is that if we run the fuzzer for, let's say, less than a day, then all the unclamped functions never get any meaningful coverage. And we also don't do state space enrichment, which you mentioned. So we're also not even rewarding the fuzzer for it. Whereas what we tend to see is if we let the fuzzer run for maybe 4 days or something like that, then at the beginning we get all the shortcuts to work. And then after a few days, the fuzzer eventually adds them. But do you feel like us just spamming clamped versions or shortcuts is technically making the fuzzer not reach the other unclamped handlers because we're basically rewarding it that much? So there is a downside, basically.
Yes. And this is another conjecture. Again, something that I wish we could at least prove for a certain set of programs. Like we can say, I think intuitively, adding clamp functions is going to make it so your unclamp functions never work intuitively. I can't prove that, but I'm pretty sure it's true. So I think the right way to do this is to first have a harness with only unclamped functions. And then once you're satisfied that you've gotten as much as you can get out of that, move to a harness that has clamped functions included. But you still want the unclamped ones there at the same time. And I think that might give you the results that you want in less than 4 days.
Yeah.
One thing to think about this is that it's either you want to have the further doing the broader coverage possible and reaching weird things within like the broader sense, or you want to narrow down a bit more the exploration and guide further toward specific action, toward specific kind of step that you have in mind. You cannot really do both at the same time because just of like like the exploration limitation. So what Ben was saying, it makes totally sense where you can use both modes. Like sometimes you just do like a broad exploration, increase the corpus with that, and sometimes you do like a narrowed exploration with some guidance to the further that you can explore specific state.
Amazing. So we have a couple of questions. I think we're stimulating the convo. This is a great convo, by the way. This is amazing. So we have a quick question by Gunjan. Sir, what is canary flaws? What is a canary flaw? If you want to re-ask it, Gunjan, try again. But perhaps, Benjamin, if you want to give it a shot.
What could be a potential flaw in a canary? Is that the question?
Sir, what is canary flaws?
Well, okay, so adding a canary isn't always good. We kind of touched on this a couple of minutes ago, but let me actually find the big thing of code. So let's say, so when we were doing this earlier, we added this little canary here, where if there was a donation and a swap in the same sequence of actions, we want to mark it interesting. We want it added to the corpus. If it turns out that the reason that we thought this was interesting is wrong, so it turns out that having a donate and a swap in the same sequence, it's not a big deal. It's actually a very normal thing. It's not that interesting. What would happen is you would be adding this sequence to the corpus, And now every X% of the time, the fuzzer is going to be trying to mutate this sequence that isn't interesting and trying to do something interesting with it, and it's not going to work. So now your fuzzer is spending like 10% of its time executing this sequence that isn't interesting. So it is possible to add a canary that ends up being like totally a terrible idea. You got to be very careful when you do this. And full disclosure, we didn't have a canary that does this specific thing. I modified the code for this presentation so it isn't like 100 lines. You want to be very careful about what you do add canaries for, because if it's not interesting, it's going to waste the fuzzer's time.
Amazing, great point. So we have another question. Just to clarify, do shortcut functions include the entire sequence of functions that need to be called before executing the final swap function? So would you do an entire shortcut, or would you also have shortcuts that are in some way partial?
We do have a couple of partial. So technically this first one right here, initialize, pair, and add liquidity, this is a partial because it doesn't get all the way to a swap. It just sets up the pair. And we have a couple of others other than initialize, pair, and add liquidity. We have one that adds liquidity so that it's very tightly focused between like 0 tick and 1 tick. We have one that adds liquidity across the entire tick range. We had a whole bunch of these, and like sometimes they would have run actions at the end, sometimes it wouldn't have run actions at the end. At one point, there was this potential issue in Uniswap where the fee growth variable, it's called, I think, fee growth X92 or something. They were concerned that it would overflow twice for the same sequence. And the problem is, if it does overflow twice during the same sequence, during the same transaction, it would allow you to steal funds. So for something like that, we would want as much interesting stuff before we run actions as possible. And so we would have a bunch of shortcut functions that did things, but we wouldn't have the run actions quite yet. Or instead of having run actions, we would always add a shortcut settle before calling run actions. And that'll make sure that if this situation is even theoretically possible, this transaction will succeed. I think that answers the question. I don't know if I got off in the
Yeah,
bushes.
I think it's cool. Yeah, and I think you answered the question. So yeah, and I think I definitely see the parallel in other types of suites where you will do an initialization or possibly even redeploy the entire system with some clamped config just as a means to have it try something else. We now have a question by the anonymous attendee. They ask, I think the question may be, what is a canary? Would a canary be adding some line of code in the code base to have a log trace? Or like, would you distinguish at this point, or would you just say that state space enrichment literally means just put some extra lines so that the fuzzer is rewarded?
So state space enrichment and adding a canary here is about adding a branch. Technically, this log doesn't have to be here. Actually, it might have to be here. I'm not sure how Solidity's optimizations work off the top of my head, but the only reason why there's any code here is just to make sure that Solidity doesn't optimize this conditional away. What's important is your canary has a branch. If it doesn't have a branch, if let's say this if statement wasn't here, then this string is always going to get covered when going through this function. It's not going to matter. It's having this branch here that tells the fuzzer, hey, there's something new here that you didn't find before that is now being covered. That's interesting. And that's what ultimately that's how things get added to the corpus. Like if you just execute something and there's no new lines of code that are being covered, then as far as the fuzzer is concerned, what it just executed isn't interesting. It's only when it hits brand new lines of code that it's like, oh, this is interesting. I need to be able to like replay this or mutate it later, and it adds it to the corpus.
So I guess to be devil's advocate, why I guess wouldn't the optimal way to make sure it doesn't get optimized and it always works, wouldn't it be to literally just put a counter that increases by 1? versus like I guess why would that be, I guess, dumber compared to a log string or a Boolean canary?
You could do a counter. You could put anything you want in here. The only thing that matters is that there's a branch. Um, like this could be all kinds of different branches. One type of branch that might be interesting is if there's two swaps in the same sequence that occur for the same pair. I think that would be really interesting. And maybe the way you implement that is just having this be an integer instead of a Boolean and like plus plus it. And if this is larger than 2, then emit log string. All that really matters for the canary to exist is that there's some kind of branch.
Yeah, yeah, that makes a lot of sense, and it's a really interesting aspect because I feel like you called it the hidden conjecture, but I feel like it's basically a design decision of these tools, where if you make it a bit more explicit, then you could probably write a tool with a different conjecture that
Yes.
possibly would behave differently for this context.
Yeah,
If
and I
you
think I was going to say
go
over
ahead.
yeah, over the long term, the goal is that you don't have to think about canaries at all. Because like normally I wouldn't add canaries, but this is like such a unique case where so much of the fuzzer was just not working anymore that we really had to go hard with the canaries and make sure that certain types of parts in the state were covered. You could do an entire fuzzing campaign without ever doing a canary and it'd be okay. Over the long term, we kind of want the fuzzer to be able to identify what's an interesting state itself without you having to be able to explicitly tell it that. But that's still like a work in progress.
If you remember the presentation I was doing a couple of like hours ago now, there are a lot of nuance into fuzzing, and here we are using a coverage guided based on instruction, which means that the fuzzer is trying to increase coverage just purely on instruction. But it doesn't mean that in the long term this is all it's going to do. There are a lot of kind of techniques and different strategies that a fuzzer can do to increase its chance to find a bug. And as of today, it's a most kind of like basic and like a first baseline we can have is coverage based. But as you are hinting, there are probably other strategies. There are probably other algorithms that we will be able to implement over time.
Yeah, that's amazing to hear. And yeah, I mean, from my end, I guess we're going into inside baseball a bit, but um, yeah, the real question is always whether to spin up your own fuzzer and why. I think this could be an idea, although maybe that's more for the Uniswap team to handle. I think we had one last question, which was how much time do you spend just tweaking coverage versus running the fuzzer once you're content with coverage?
That's a really good question. Um, it's really hard to put a finger on it because like a lot of the time it's not even a matter of like tweaking coverage. It's a matter of figuring out why the fuzzer is finding a counterexample for, a certain sequence. Especially with Uniswap because the protocol was so complicated, it's very easy to like write all of our properties and miss an asset somewhere or miss a liability somewhere, and for some whatever reason our entire test suite is failing and we can't figure it out. So I'd say that probably dominated most of the time. I'd say like maybe 30 to 40% of the time, maybe even 50%. And I'd say the rest of the time was 25% between trying to make sure our coverage was really good and running those tests at the end where like we try to add one, where is it, like adding canary flaws. But to be honest, we didn't start adding canary flaws or like testing them until the very, very end. I'd say we only spent maybe 5 to 10% of the total time doing that. And it may not be thorough, to be honest. Like if you were to go into it today and add one to a certain spot, there's a chance that that's a spot that I didn't try to add one to, and it might not cover it as well as it should. And that's just the reality of like working in a time box like 3 weeks. You can't do everything.
Yeah. I mean, what I'm wondering is obviously if you had infinite time, whether you would have like opened up the UniV4 code base into, I don't know, libraries or, some weirdness, But let's, I guess we'll have one last question from the um, audience. What are some of the techniques that can be incorporated to help the fuzzer automatically identify interesting paths? Do you feel like there's something else past the state enrichment that you mentioned?
Oh yeah. Oh yeah, absolutely. This is something we've been working on a lot recently. Um, so, oh man, I don't have any code in this presentation I can use. Let's say you're trying to figure out if a number is larger than another number. What the fuzzer could do theoretically is when that inequality comes up in the sequence of like, EVM opcodes being executed, it can see how far off one thing is from another and see, oh, we're really close to breaking this invariant, or we're really not close to breaking this invariant. Let's try, if we just got closer to breaking this invariant, maybe we try to do the same mutation that we did a second time and see if we get even closer. There's a whole bunch of things you can do on the fuzzer side to further enrich the state. But the challenge here is when we think of these things that we think should make sense, we're still making a conjecture and we don't know how often that conjecture is going to be true. And so what happens is you might spend a whole bunch of time implementing this new conjecture that you think is going to absolutely do, it's going to improve coverage 100 times over. You do it and you see a 5% drop in your coverage. Sometimes it's very not intuitive what you think is going to increase the state space and like improve the fuzzer versus what doesn't. But yeah, there are a lot of other ways to do it, and it's very application dependent. So if you look at the techniques that you use in traditional fuzzing like a C program or something, the techniques that they use are completely different than the techniques that we use because the programs that they run, they always start in the same state. They don't have any kind of dynamic behavior based on what happened earlier. Whereas in smart contracts, this is something where it's deployed. You don't know what state it's going to be in when you call it. And so we have to use completely different techniques than they do.
Yeah, in
Amazing.
fairness, it's a full new area of research here in terms of, okay, what heuristics are going to be useful. We are exploring a couple of new heuristics, but what we have also been doing over the past months is to build an internal benchmark which allows us to compare what's actually useful. Because as Ben was saying, you might have like a cool idea, oh, okay, we should do like that to increase coverage or to increase kind of like the exploration. It might work for your code base, but is it going to work in a more generic and general case? That's a difficult question in fuzzing. So that's why we are exploring different ideas, but TBD which one is going to be actually delivering good result.
All right, we'll do literally, we're gonna close the event at 45 no matter what, but let's entertain this last second question. How do you, I guess, when do you choose Echidna versus Medusa? What's your current heuristics?
Right now, I use Medusa 100% of the time. And that's because I'm trying to develop it more and figure out how to improve it. During this engagement, I was 50-50. So sometimes I would be actively using Echidna and running Medusa on a long-term task. Sometimes I was actively using Medusa and running Echidna on a long-term task. It's like the thing is like the conjectures that each fuzzer uses, like the heuristics, aren't exactly the same. So what Medusa is able to find, sometimes Echidna can't find, and vice versa. So for some period, I was, basically using them both evenly. And the goal here is still like long term, we only use Medusa. But the trick is like they both have their own heuristics that work for certain cases, and we don't necessarily know which heuristics to add to Medusa to make it a superset of Echidna quite yet. But we have some ideas in the pipes that are like in the works. But it's like at this point right now, they both are good at finding certain types of things.
One way to think of that is that if you're going to fuzz something for the next 3 months, it can be okay to use both. If your plan is to fuzz something for like a year, use Medusa because this is the one that is going to be the most developed in 2025.
Amazing. Honestly, this talk was a total banger, 10 out of 10. Amazing. I feel like it's also getting some of the more professional people to think about stuff. If you have any last second question, guys, drop it in the QA. What we're gonna do in a moment is we'll just do like a closing ceremony. So even if you drop the question now, maybe our guests will, panelists will answer in the chat anyway. So that's another thing. Were there any vulnerabilities? Do you guys find anything you would want to share from the UniV4 engagement?
So the report is public. There is one low severity bug that we found indirectly from the harness. So it wasn't directly from one of the properties in the harness breaking. But like, as I mentioned before, there was a situation where properties were being broken and we didn't understand why they were being broken. And it turns out there's some kind of behavior going on in Uniswap where, like, there's a fee that we're not keeping track of or something. And so our low severity issue that we had on our report was indirectly found, but it wasn't like because a specific property was broken.
Gotcha. Yeah, have you ever had any experience using Sartora recently, Benjamin?
Not recently, no.
All
Why?
right.
They do something fun?
Well, I guess we'll tease possibly, and I'll reach out to all of you before, but possibly, maybe in a few months, we're gonna have like a really good 3 hours FV versus Fuzzing Ultimate, the type, Avengers type panel. So maybe that's when we're gonna all be using Sartora and all using the Fuzzing just to debate it. So maybe that's how it's gonna go. I guess I'm gonna start the closing ceremony. I appreciate all of you guys for joining us today. Here, overwhelming. So fundamentally, I want to give a big thank you to the people at Trail of Bits, Josselin, Benjamin, Anish, Gustavo, Emilio, Arthur, and David. They fundamentally built all of the open source stuff we've been using for over a year. So only love from us. There's the meme of, the little egg keeping us all of the industry working. And to me, it's really the people at Echidna, the people at Chimera, the people at Echidna, the people at Medusa. I also want to shout out the people at Perimeter, one of the best discords if you want to chat about the pausing as a profession. They invited Daniel to do his talk. And I also want to shout out our team at Recon, Antonio, my co-founder, Alberto, Nicanor, Simon, and Lawrence. Thank you all for helping us build this tool, but also build this community. And hopefully together we can make Buzz a thing of the past. So that was Fuzz Fest. You guys have an amazing rest of your day. Hopefully, I'll see you soon at the next one.